The story started with black holes, and with Jacob Bekenstein, who derived an equation to describe their entropy. A black hole's entropy represents the amount of quantum information of everything that ever fell into it. This Bekenstein bound represents the maximum possible entropy/information of any volume of space. Oddly, that maximum is proportional to the surface area of that space, not its volume. And that was surprising. Surely the information in a volume of space depends on that volume, like 1 bit per infinitesimal voxel, not 1 bit per pixel on the surface. Stephen Hawking confirmed the Bekenstein bound by calculating the amount of information leaked by a black hole as it evaporates in Hawking radiation. His discovery of Hawking radiation led to the black hole information paradox, because this radiation was expected to erase the quantum information of everything that fell into the black hole. But destroying quantum information would break the foundations of quantum mechanics, hence the paradox. This conundrum inspired Gerard 't Hooft to show that the information of all material that fell into the black hole could be imprinted on that outgoing Hawking radiation. And while it's waiting to be radiated, that information should be encoded on the event horizon of the black hole. Nice solution, but new paradox. Things that fall into a black hole do actually experience crossing the event horizon and being inside the black hole. So the interior of the black hole has a dual existence. From the point of view of outside observers, its contents are smeared into 2D on that surface, but from the POV of anyone falling in, they are definitely inside the black hole, plummeting to their doom in full 3D glory. This is the first glimpse of a holographic spacetime, a 2D surface that encodes the properties of the 3D interior. 't Hooft, along with Leonard Susskind, extrapolated this to propose that not only is any surface sufficient to describe the locations of all particles in its volume, but also the full machinery of that volume can exist on the surface, all degrees of freedom needed to describe the behaviour of everything within. But it's one thing for this stuff to fit on the surface, but how is it actually encoded? How does the 2D surface store information about that extra dimension? And how do interactions on that surface correspond to interactions in the volume? Leonard Susskind laid out the first steps to how this could be achieved using string theory. But ultimately, it was Juan Maldacena who figured out a concrete string theoretic realization of the holographic principle with ADS-CFT correspondence. But I'm getting ahead of myself. Let's ignore string theory for the moment and just think about how to create an extra dimension. Let's say we start with a plane, a flat 2D spacetime. Now, grid it up into a lattice of cells and make a set of rules about how those cells interact with each other. Those rules are a field theory. The lattice itself is the field, and the cells are some elementary component of the field. But perhaps they're not the smallest possible component. For now, let's just say the size of those cells depend on how we're looking at the grid. For example, the resolution of our microscope or the power of our particle accelerator. Probably the rules between cells, the field theory, depends on their scale. Focus on a very small scale and we see a very fine grid that interacts according to one set of rules. Zoom out and we see a coarser grid with cells that are the average of smaller cells, but which presumably interact via different rules. Or so you'd think. But we're going to add something weird. We're going to say that our field theory is scale invariant. We'll say that the rules are the same for small pixels or big pixels. We see this scale invariance in fractal patterns where the rules defining structures repeat to infinitely large or small scales. We also see it in string theory, which I'll come back to. A field theory with this property is called a conformal field theory. In the last episode, I said that a conformal transformation is one that leaves all internal angles unchanged. A conformal field theory has this property. For example, you can change the scale at every point on the grid separately and not change the internal angles or the shapes of the pixels, which corresponds to not changing the rules of interaction. By making this conformal field theory, we've added asymmetry, invariance under local changes in scale, also known as Weyl invariance. This adds a degree of freedom everywhere, like a new infinite number line at each of the 2D grid points. Objects on the 2D grid also have values on that number line. They exist at a certain scale. If objects at different scales don't tend to interact with each other, then this new degree of freedom behaves like just any other dimension. Our 2D grid behaves like a 3D volume, and we can treat it like one, at least mathematically. You might say it's not a real 3D grid because the third dimension is fake. But is it? What is a dimension but a number line of possible values which A, exists alongside the other dimensions but is independent of them, B, over which the rules of physics stay the same, and C, imposes some kind of locality. For example, elements of that number line need to be next to each other to interact. Crudely, this is how an extra dimension can be coded in a holographic universe. But for the details, we need string theory. Even from the beginning, string theory had hints of this scale invariance and dimensional weirdness. The first iteration of the theory, around 1970, tried to model the strong force between pairs of quarks, mesons, and this strand of gluons that behaves like a vibrating string. A nice feature of this model is that changing the length of the strand, which defines the energy in the bond, doesn't change the basic physics. That means you can pretend string length/energy is a separate dimension as a calculation trick. The weird thing is that when you write the quantum wave equation for the gluon strand with length expressed as a separate dimension, you get the wave equation of a graviton, the quantum particle of gravity, which is ridiculous given the puny energy scale of the meson. Gravitons shouldn't even exist there. This and other glitches led to string theory being abandoned as a model for the strong force, but it was quickly rejigged to make it a theory of quantum gravity, and the scale invariance of the strings became a central feature of string theory. Fast forward a couple of decades to the 90s, we now have several versions of string theory that try to explain how vibrating strings can lead to the familiar particles of the universe. These were tentatively united by Ed Witten's M theory, which showed that different types of string and string theories were all related by dualities. A duality is when two seemingly different theories prove to represent the same underlying physical reality. These arose from the way string size and energy scales could be rescaled. But the strangest string duality was still to come with ADS-CFT correspondence, proposed by Argentinian physicist Juan Maldacena in 1997. Strange because it provided the first concrete description of a holographic universe. Maldacena imagined a set of string theory objects called branes. These are like multi-dimensional strings that can serve as start and end points for strings, but also as spaces embedded within higher dimensions. Maldacena considered geometrically flat 3D branes. These branes are extremely close together, basically overlapping. The strings connected to these branes are scale invariant, so their length and energy can vary without changing the physics. Under certain assumptions, he found that the resulting brainy structure looked just like a Minkowski spacetime of 3+1 dimensions on which there lived a field theory that arose from interactions between brains. In itself, that field theory wasn't stringy, rather it was a quantum field theory like the ones that give us our standard model of particle physics, a Yang-Mills theory, but with supersymmetry added in. It was also a conformal field theory, a CFT, so it was invariant to the scaling of grid sizes. This quality came from the energy scale invariance of the strings embedded in the construction of this space. In good old string theorist style, Maldacena defined a new spatial dimension that incorporated that invariant scale factor. The 3D space became a 4D space. While the original space was flat, the new space had negative curvature. It was a hyperbolic anti-de Sitter or ADS space. The conformal field theory in the original space included no gravity, but in the higher dimensional space, gravity emerged, revealing a full quantum theory of gravity. This is the ADS-CFT duality. As with the other dualities in string theory, this one was extremely useful for calculations. When interactions in the lower dimensional field theory are extremely strong, we would say the fields are strongly coupled, then the corresponding higher dimensional gravitational structures would be weak and solvable. Conversely, strong gravitational fields in the higher dimensional space, like in black holes, look like solvable configurations of particles in the low D space. Among other things, this provided a new resolution to the black hole information paradox. The information lost in a black hole persists perfectly comfortably in the lower dimensional space. And the techniques of ADS-CFT correspondence are even extended to disparate fields like nuclear and condensed matter physics.
So a lot of people have worked on this thing which I'm going to show you called the fuzzball paradigm. I just put some of the people who are actually working on it right now, and I want to show you the kind of picture which actually emerged. And the picture is interesting because it will lead to a radical change in what we think the black hole looks like. And from what we've been saying, you can already guess what we want the change to be. We don't want the black hole to be such that everything has gone to the center and there's just the vacuum outside. We really want a surface there. And our problem is whatever you put there, it just falls in. And now let's see if we can get past that. So in ordinary particle physics, particles can be thought of as little dots. But in string theory, as you might guess, objects are strings. Instead of particles, you have strings. So they are what are called extended objects. They have size. And they can be, instead of one-dimensional objects, they could be two-dimensional sheets or three-dimensional sheets. Those are called branes, like sheets are just called branes and so on. So you have lots of objects. But the important thing is they're not point-like. They have a size. So why does size matter? If you have an object with a certain size, there are two things that you can do to it when you add energy into it. If you put energy into a point particle, it just goes faster. It's kinetic energy. If you put energy into an extended object like a string, there are two choices. You can either make it go faster, or you can use it to stretch the guy. And now you see something interesting can happen. When things fall into a black hole, they just rush in, and they go to the central dot. But if you take a lot of mass to make a big black hole, it's possible that if the black hole is made of strings, a particle just rushed and made a black hole. If it was made of strings, does it really have to go here? Or if the energy actually goes into stretching the string, but then it's different. The more energy you put, instead of becoming more dense and trying to go in, it may want to stretch and expand. And if it expands enough under that stretching, it may never actually fall into this critical radius and ever make a black hole. Maybe it always remains like a ball. Let's just see what happens. So what actually turns out, when we start looking at these calculations in string theory, we found that instead of actually going down to a point, the energy actually goes into stretching those guys. And as they stretch, they become big. And the way the numbers turn out, the size to which these objects become is just comparable to the size which we thought this entire horizon would have. So they're not shrinking. Somehow in string theory, you are not getting the black hole. Well, let's explore the structure of this a little more. If there's so much gravity in here, why isn't it pulling the surface in? What's holding it there? That was the whole point. You can always make a blob, but everything gets sucked in. Why is it not falling in? That's the real crucial question, and I want to show you why the thing is not falling in. The reason it's not falling in really uses a very important property of string theory. As you know, string theory lives in 10 dimensions, but we only see 3 space and 1 time dimension around us, and what that means is there are many extra dimensions. They're just very small. That will be like little circles, so we can't actually take a walk in them, but they are around us and they are tiny little circles, and normally you ignore them. They are in this room, they are everywhere, but they're doing their own business, little circle, but as we walk, we don't actually crawl around the circle, we just go like this. But now you'll see that something will actually happen because of the extra dimensions. So just to first recall our puzzle, we have this mass in here. If you come within the critical radius, this is the critical radius, your net energy, mc squared minus the gravitational potential energy, would be negative. That was our puzzle. Instead of trying to draw a picture in 3 dimensions, let me just draw one space dimension for simplicity. I just drawn it as a line, and it's the same puzzle. There's the mass, this is the critical radius I marked out on both sides, the horizon radius, and if you come in here, you have net negative energy. Just the same puzzle, I just drew one dimension for simplicity. But now if you have extra dimensions like this little compact circle, there I drew it for you. And now the dimension, the whole thing looks not like a line, but like a drinking straw. Okay? It looks like a drinking straw. And up to this point, people were, of course, aware of compact dimensions for a long time, so they didn't do anything with this. It looked like something pretty irrelevant, because the compact circle would be something like Planck size. This whole structure of the black hole is like several kilometers. So who cares? You still put a mass in the middle. There'll still be this horizon on the 2 sides. And if you come in here, you should have negative energy. People thought the compact dimensions really made no difference. But actually, there's something you can do with the straw, which you couldn't have done with the line, which is radically different. And let's see what you would do. Take the same straw as before. And this was the radius we call the horizon radius. Take a pair of scissors and chop off this piece from here and throw it away. The entire interior of the black hole is not part of space-time. We'll discard it. Now, how can you just chop off a piece of space-time and lose it? What about the open ends you get? You can't just come up to there and then say, I have no place to go. You can't fall off the edge of space-time, but you won't. Because you take this edge, you can close it off smoothly like a cigar with a cap, and you close this thing off with a cap. And now you can see you have a completely smooth space-time. If you come from this side, you don't fall off the edge. You come here and you go back here. And you come from here and you go back here. But there's no inside to fall into because there is no inside. This is a whole new topology. And you didn't have this possible topology if you didn't actually have this extra dimension. If I just had a line and I threw off the middle segment, when I come to that endpoint, I will fall over. But if I had an extra dimension, I have a smooth cap. I come here and I go right back here. And this is the actual structure of the black hole that you get in string theory. So if you actually take a lot of mass and you accumulate it, instead of getting the kind of picture I was showing you before, where you simply have all the mass sitting here, and there's a horizon, there's a region where you can put negative energy things, the whole thing morphs into something else because these strings stretch, they're going to change everything. What do you get at the end of the day? What you get at the end of the day is this structure. And what happened to all the mass that you had, the red dot in the middle carrying all the mass of the black hole? If that middle region is not there, there's no place for that mass. But this region is curved. And gravity, mass, and curvature are connected. And this curvature over here costs energy. And through the relation E equals mc squared, all the energy in this curvature, that's what the mass of the black hole was. So this is the actual structure of the black hole you get in string theory. And you can see it's radically different. But with this new structure, this was in the one-dimensional example, but now you can see how it looks like in many dimensions. Suppose you take this room, and you want to make a black hole in the middle. We'll take a whole ball from the middle of this room and throw it away. It's not even part of space-time. But now suppose you come at it from any one direction. Previously we had only 2 directions. Now I can come at it from any angular direction. As I come near that end, I can just put this cap in there. So I come there, I don't fall into that hole. I just come there and I go right back. I come this way and I go right back. And when you actually look at what states the strings make in string theory, when you put the mass enough to make a black hole, instead of shrinking to the usual thing with a dot in the middle and a vacuum around it, this is what you actually end up getting. I just draw this picture like this, but remember this is not part of space-time. There's nothing there. Space actually ends here, and I just draw this wiggles to just show that something happened as you came near the surface. This quantity, this object you get this way is what we call the fuzzball. So we find that all the states of the black hole, all the different things you could do with the strings to make a black hole, they all have the structure of fuzzballs. There are actually many, many different fuzzballs, because when you actually add this cap in there, you can put the cap with many different shapes. It doesn't have to be just a simple round cigar. You can actually have a clockwise twist or an anti-clockwise twist, just something a little technical, but I just put here with pluses and minuses. So in every different direction, you can choose a clockwise or an anti-clockwise twist. There are many different possible states for the black hole, and that will be very important in a minute. So here's another depiction. If you just had a star, it bends space-time a little bit, curves it. Normal picture of a black hole was that you get a horizon, it tears a hole in space-time, and there's a singularity inside. But now actually the horizon never forms. The whole thing ends here. There's no inside region. It's just like a surface of a star. It sort of just ends here. And this part over here is what I was drawing you as a fuzzball. This surface is this surface over here. And there's no inside to the black hole. There's no singularity. All the problematic things. A singularity was a terrible thing to have in a real theory. It's gone. The horizon was the one creating all the troubles by having this pair production. That is gone. And we actually see the states. And now let's see the crucial question. We at least resolved the information problem, because in a planet we had no information problem. It radiates from its surface, and the atoms really see what's there and carry out the information on the surface. The same is true for the fuzzball. Different fuzzballs have different shapes, and the information goes out from the surface, and you don't get the usual thing where everything makes a vacuum around here, and the actual radiation happens from particle pairs being pulled out of the vacuum. That process is not the true process of how black holes vanish. That looks like a beautiful solution. So you might say, with string theory, we have come and solved the problem. But we had this about 10 or 15 years ago, but not everybody was convinced it's the right answer, because after all, this is a radical change in the structure of the black hole. And you should ask a logical question. If quantum gravity normally operates at very small distances, the normal scale of quantum gravity is supposed to be 10 to the power minus 33 centimeters. A black hole is like several kilometers in size. Why would quantum gravity come and change something on these scales? That's the question we have to answer. If we really can understand why this happened, we would really have understood how such a thing could ever happen. But people also didn't focus on the fuzzball construction that much in the beginning, because they thought they had an alternative solution. It's very interesting that they thought there was an alternative solution to the problem, but now we know that solution wasn't right. But it's very interesting to know what that alternative solution was. And it's something called the idea of small corrections. So what's the postulate of small corrections? We did say a pair came out of the vacuum, and the vacuum is the same for a star of one kind and of another kind. But in any case, there could be a small difference between them, because the vacuum of one, there could be some small long-range effects. We said this is very far from this. It could be 3 kilometers for a solar mass black hole. There could still be small differences. I've drawn some rather large differences here, but just to show you. But they could be a little bit different. You can see that over here. Now, suppose every particle that came out had a little bit of difference, depending on whether you had a red dot in the middle or a blue dot in the middle. It's still coming out of the vacuum, but you could say there's a small difference in there. But so many particles are going to come out before a black hole evaporates. There will be trillions and trillions and trillions of particles coming out. Could it be that there is some delicate encoding of data in these small little corrections, which in the end actually capture all the information of whether you had a red dot or a blue dot? If that could be true, then Hawking was making a fuss for nothing in 1974, because you do first a leading order calculation and you see information not coming out, but maybe you never took care of the small corrections to your calculation. And if those corrections were enough in number, because there are so many particles coming out, then maybe the information was there all the time. You just didn't look carefully. And in fact, there was no Hawking paradox. And in fact, as it turned out, in 2004, you might have heard in the press that Hawking surrendered his bet, which he had taken with John Preskill. Preskill had been saying information is not lost, though I don't know how it's not lost. And Hawking and Kip Thorne, another relativist, had said, no, information is lost in black holes. And Hawking said, I think maybe these small corrections do finally, maybe they do the job, so maybe it's okay. And so he paid off the bet, which was a bunch of sports encyclopedias, and he actually sent them over to Preskill. And Kip Thorne actually refused to pay. He said, look, you haven't shown me anything. If you want to say that these small little corrections somehow invalidate a real argument, at least show me that they do that. But it's very hard to actually check that, because so many particles are going to come out. Each one can be subtly different in some way, and you have to check whether they can or cannot encode the information. How do you ever check such a thing? So it's very funny, a situation that two leading physicists, one agrees that he might have been wrong, and the other says, I don't agree, and they couldn't resolve it. But you can see why it's a difficult thing to resolve, because you don't even know what corrections you need. So it turned out that there's a very interesting theorem in quantum information theory. It's called the strong subadditivity inequality. It's by two people called Lawh and Ruskay. And this theorem actually has a lot of power, because it tells you how you actually encode information in delicate quantum correlations. There's some inequality in how much you can encode by what you can do, and that's why the inequality you can see this inequality sign. And if you had many systems, A, B, C, and D, how do the informations correlate with each other? That's contained in this theorem of quantum information theory. And it turns out if you actually use that particular theorem, you can prove, which is something I managed to do in 2009, that it doesn't matter how you try to make little delicate corrections to each pair, you actually cannot solve the problem. So for example, if you make only corrections of 1% at each step of the emission, even though you might emit trillions and trillions of particles, the number of particles doesn't really matter. You'll never get more than twice that information. If you put 1% corrections, you'll never get more than 2% of the information out. You can prove that by this inequality. I just wrote that in this slide. If the corrections at each step are of order epsilon, epsilon could be like 0.01, 1%, then the fraction of information that can be encoded is less than or equal to 2 epsilon. This will be 2%. So then you actually cannot fix it by this method. And so now we have a real problem. If we don't completely change the structure of the black hole, we can't solve it. And because the problem always was that you couldn't change the structure of the black hole in classical physics and ordinary physics. But with string theory, we have changed the structure. This theorem proved you do need to change the structure completely. Small corrections won't do it. In string theory, you found in all the cases you worked out the structure does change, so you might as well take that solution. So that's why I think the fuzzball solution is the correct one. Even though it looks like a radical change to the physics, in string theory, every state you try, it always swells up into a fuzzball. It's true we can't check all the states for all the black holes. It's an enormous technical problem, and we can't check that. But we know that we need that change there. Small corrections won't do. We need a complete change. And in all the examples we work out, we do get the complete change. So it looks plausible to assume that all states of all black holes are actually fuzzballs. Now we come back to the question I was just mentioning to you. You still have to explain to somebody who is a skeptic, how did physics which happens at the quantum gravity scale, string theory is supposed to not change anything on the scale of meters, or in fact, in this case, kilometers, and yet somehow we are finding that everything has radically changed all the way up to the horizon, and the horizon could be very big for the mass, for the mass 1 million solar mass in the center of our galaxy. For that kind of a black hole, the radius is about 1 million kilometers. There it has changed over 1 million kilometers. So we have to answer this question, how did quantum gravity become so important? So here's the puzzle again. The black hole is an astrophysical sized object, and quantum gravity effect should operate at this tiny scale. And for a solar mass black hole talk of 3 kilometer distance from here to here, how can the structure change so radically? For that, we go back to what I was mentioning at the start of the talk, the work of Jacob Bekenstein. So Bekenstein had noticed an odd fact. You might have heard about the second law of thermodynamics, which says that entropy always increases. Entropy is the amount of disorder in the universe, and that doesn't go down. It can only go up. But here's a funny thing you can do. Take a box containing some gas, and that has some entropy. And you take that box of gas, and you throw it into the black hole. It will go inside. It will disappear into singularity, and there's the black hole. It's gone. So well, now you can't see the gas. So have you decreased the entropy of the universe? Have you violated the second law of thermodynamics? Now, nobody wants to violate the second law of thermodynamics. They love that law. Okay? So what has gone wrong? Well, obviously, it doesn't look like a good argument so far, because you could take the box of gas and throw it into a trash can and close the trash can, but you haven't decreased the entropy of the universe. The entropy of the trash can has gone up. So the entropy of the black hole should have gone up, and what he noticed was, well, I can't see entropy. That's the difference. In the trash can, if you look in, you will see the gas, and you can see the entropy has gone up. In the black hole, it all goes to a dot, and you can't see anything. That is true. But at least the black hole has become bigger. So you should at least know how much entropy you should assign to the black hole, though you can't actually see what's causing that disorder. There doesn't seem to be any disorder. It's so orderly, it's just empty, all except for the dot. But in any case, you should assign some entropy to save the second law. And what he found was there's a very precise formula. If you give it an entropy proportional to the area of this surface, in fact, measured in units of Planck length squared, if you put all those numbers in, you get just the right entropy, so that when you try to decrease the entropy of the rest of the universe by throwing something in, the black hole becomes bigger, and the entropy of the black hole compensates for what you lost over here, and you have saved the second law of thermodynamics. What a beautiful argument. You cannot see anything inside a black hole. You thought you had no way of ever defining or even assigning an entropy to this guy, and this simple argument tells you not only should the black hole have an entropy, you even get a number. If you want to save the second law, you know exactly how much entropy it should have. But this actually raised another puzzle, which is what I had said is the puzzle raised by Bekenstein's work. As we said, entropy is a measure of disorder. The atoms in a gas can be in this position, or that position, or that position, and the number of different positions they can have, if that number is n, the log of that number is called the entropy in the box. How many states does the black hole have? It seems to have just one state. Everything has gone to a dot in the middle, and the rest is empty. If I put 1 for n, what is log of 1? Actually, log of 1 is 0. So in fact, we get a 0 entropy. On the other hand, we had a formula for the entropy on the previous slide, and there you can see it again. And if you put in all these numbers, notice there's an h bar at the bottom, the Planck constant, which is very small. And if you put all these numbers in, and there's a c cube at the top, speed of light cube, that's a very big number. If you put all those numbers in properly, you find the entropy of the black hole is actually huge. A black hole should have 10 to the power of 10 to the power of 77 different possible states. And here we find it has only one state. Something has gone wrong. It's even much bigger than the mass than the entropy of the sun. The sun has only 10 to the power 10 to the 58 states, because the power of a power, this is very tiny compared to this. A black hole has an enormous entropy, and we can't see it. So this was the puzzle. What is the entropy of black holes? Why is it so large? And what does that imply? So Bekenstein was sitting with this puzzle. He could assign entropy to the black hole, but he couldn't see what were the different states which were giving him that entropy. But now we can actually see what it was. We in fact have all these little structures on the side, and if you count how many these are, you find they're exactly the right number. In all the cases where we can explicitly check, they exactly give you back the Bekenstein entropy. We can't check them for all kinds of black holes. That's difficult to do. For the simplest ones, where you check it, you get exactly the right number of these states. So now we understand what we were supposed to be counting. But this time we actually have a surface. It's all the different possible surfaces that we are counting. And that makes perfect sense so far. And now let's see if we can try to answer our question, why did the black hole change so radically? So if you have just classical physics, you have a star, it shrinks under its gravity, it goes to a point. We've done that before. Why should that change? Well, so you take this particular star, and as the star is collapsing, there's a small quantum mechanical fluctuation possible where it changes into the state of a fuzzball. Well, of course, that's a sort of trivial statement. There's a small probability for anything to happen in quantum mechanics. There's a very tiny probability that I'll just vanish from here and appear on the other side of this wall. It's called tunneling. But why don't I worry about it? Because the probability is so small. It's just a fluctuation. So of course, everybody knew that anything can fluctuate to anything. Why would you care? But now there is a funny thing which is happening. This is, of course, a very small probability. It's a very massive object going to another very massive object. There's almost no probability of happening. But you have to multiply by all the possible final states that you want to go to. I might want to fluctuate towards across this wall to go here, or fluctuate across this wall to go here, or across the roof to go up. There are some possibilities, but there are only 6 possibilities here. Multiplying the probability by 6 doesn't do much for me. But the number of these guys is enormously large. We just said the Bekenstein entropy is so phenomenally large that we actually can't understand it. And as it turns out, if you multiply by the number of possible final things you can go to, by the very small probability of actually going to any one of them, the large number exactly cancels the small number. So that's the incredible thing which is happening. Bekenstein was sitting with this puzzle. I had this huge entropy, and I can't see any of those states. So there were 2 puzzles there really. Why is the entropy so huge? It's much bigger than the entropy of any normal matter. We have seen it comes from all the little quantum gravity scale little fluctuations over here, from all the different ways you can pinch off the little circles in space-time. But because the entropy is so large, the normal effects of quantum mechanics, which are so suppressed because they are so tiny, they get amplified because there's a small probability to do something, but the number of things that you can possibly do is very large. The large number can cancel the small number, and the actual probability becomes order 1, and this thing actually changes over to there. And then everything is different, because now the star doesn't actually end up here. There's small probability to leak into this, and overall, there's more chance to go here than to go here, and in fact, you end up getting the fuzzballs. This one gets completely wiped out. So this is how you actually ended up getting this complete change of the classical picture, and the black hole is really in the domain of quantum theory. But all because of this Bekenstein entropy, the entropy was so large, it changed something classical all the way to something quantum, and that's how we're going to solve this puzzle. Because as long as people thought the black hole is classical, quantum mechanics can't really change anything very much on the scale of several kilometers, there really was no solution to this puzzle. Well, let's then come to the final question that we want to ask. You might have seen in the recent press that people have said there's a firewall at the horizon of a black hole. So what does that mean? It was a general argument of the following kind. If you find some kind of a surface to the black hole, then you'll solve the puzzle, because then stuff can radiate from that surface like a star. If you have the vacuum there, we have seen the puzzle. Can we get a surface outside a black hole? Well, in normal physics you can't, but in string theory at least you have the fuzzball, So there's at least one example using string theory where you actually can get a surface to stay there. It can't fall in this case because of new topology, there is no inside, but we got a surface. So now you can ask, when you fall into a normal black hole, you keep going in and in till you go all the way through the horizon. It's just a vacuum. You go all the way down to the center and all the way to the singularity. But if you hit a surface out there, what happens? When you hit that surface, you just smash, you die. Does that behave like a firewall, like it burns you up? Are we really saying at the end of all this that when you fall into a black hole, instead of going smoothly through this horizon, you actually smash on the surface? So you can see this is a logical question to ask at this point. So I just drawn the question for you here. If an energetic photon is falling in here, it will just go through here. Here, this is just a demarcation boundary where the energy change sign, but there's nothing really there in the normal picture. And then you can go all the way down to the center. That was the normal picture. And now we have the surface, so it looks like you'll crash and burn when you hit the surface. On the other hand, we always love to be able to save our classical intuition in some way or the other. Everyone loves their classical intuition, and because classical physics tells us we can go in, somehow we really want to be able to go in. But this time the inside is not even part of space-time, so we can't go in. And so what's the right answer? Is there any sense in which we can even think that there is an inside to the black hole? And it's very interesting that there's a conjecture here based on some old work of Susskind called complementarity, now slightly modified to be in a way, so I'll call it fuzzball complementarity. And it tells you, even though you fall on the surface and you can't go in, and you smash into lots of pieces, you may still not feel anything, and you may still feel that you're going in. So let's see how that can happen. It's an amazing fact that there's no place to go in, and yet you might feel that you're going in. This kind of an idea is called complementarity, and it's sort of at the cutting edge of where we are. This is something we don't know if it is true or if it's not true. I hope it is true because it's a beautiful idea. It will allow us to save our classical intuition. Okay, so what's the idea over here? Sometimes two completely different systems can mimic each other. So if you go to a room and you hear the sounds of a piano, you might think, hey, there must be a wonderful grand piano over here. But when you actually enter the room, you might find, hey, there was just a keyboard. Now, a piano produces some notes by a vibration of strings. A keynote actually produces notes by electric currents going in circuits. It's completely different. And yet they actually mimic each other to a very good approximation. Well, could the same be true here? In the classical picture, you came in here, you went in, that was your system. And here you come here, you hit on the surface, and all you can do is maybe oscillate the surface. If you hit the surface of a water drop, the water drop oscillates. That's all you can do. You can't go in. There's no inside there. Can this one mimic this one? If one guy could mimic the other, or at least approximately mimic the other, then it would be like the piano and the keyboard, and then in some sense, even though we have no inside, we would mimic falling in, and our classical intuition would come back. If this was true, just see what a beautiful thing it is, because space, which wasn't there, can be mimicked by something completely different, which didn't have that space in it. So actually, the analogy to the piano is even closer, because in quantum theory, every state has an energy E. And from Einstein's work, we know that the energy is connected to the frequency. If you take light of higher frequency, it has higher energy. Like, X-rays have very high frequencies. They have very high energies. So E equals h times the frequency, Planck constant times the frequency, what Einstein taught us. And any physical system is completely characterized by its possible frequencies. So getting even closer to how a piano behaves, right? It's just the frequencies emitted from that particular instrument. Every physical object is characterized by some frequencies. For example, atom is characterized by the frequencies of its various orbits, and what it emits is given by the energy levels, which are given by this formula as the difference between two frequencies of two different orbits. And now, therefore, you can ask the question, if I give you two different systems which have the same frequencies, can you tell the difference? And the answer in quantum mechanics is no. This is kind of object is called a duality. It happens all the time in string theory. You have one kind of object which has some frequencies, a completely different object which has the same frequencies, and actually they're isomorphic, and you have a duality. One system can be replaced by the other. And now let's see how that idea might apply to what we are doing. When you fall into a black hole and you're going inside, the whole process of going inside, everything is a wave. There are some waves inside the black hole. You can look at those waves. You have to see the structure of the black hole to compute them properly. But they have certain frequencies, and there I call them frequency 1 for the black hole, BH is black hole, frequency 2 for the black hole, some list of frequencies. If you hit the surface, you can't go in, you can only vibrate that, but the vibration of the surface has some frequencies. I call them frequency 1 of the first ball, frequency 2 of the first ball, those are the FBs. I get a set of frequencies. Now what if these frequencies were to the first approximation equal to these frequencies? But then actually you can't tell the difference between not going in and just oscillating the surface and actually mimicking the idea of actually falling in. And there is reason to believe that this is what actually happens. There's reason to believe that the fluctuation frequencies, oscillation frequencies of the first ball are actually the same as the frequencies of waves which are actually falling into the black hole. So now we are reaching the final point of what we do, and the idea of how two frequencies can actually match, kind of duality, it came up in a very closely related context in this work of Maldacena in 97. If you hit a concrete block, you just smash and you die. Okay, so that we know. But if you take these brains in string theory and you fall onto it, you oscillate the brains, and they have a certain set of frequencies. But it turns out that if you just had empty space with no brains, but something called anti-de Sitter space, a particular kind of curved space, the frequencies of vibration in that are the same as the frequencies of vibrations of D brains, and one exactly mimic the other. So you can actually replace brains with space, and that's called the ADS-CFT correspondence. You might have heard about it. Maldacena is very famous for having discovered that brains can be actually replaced by space-time. And now we are asking for something very similar. There are all the different fuzzballs, so at low energies, at the temperature of the black hole, they radiate differently, and the information goes out. But when you hit them hard, when you fall onto something, energy is very high. At high energies, these oscillations are basically the same for all these guys, and they mimic free infall, and so you get the physics of effectively falling in. So I'm basically done, and let me just take a couple of slides to summarize what I have just told you, and let's see if we can wrap it all up together. So first we have seen the information paradox is very serious, and this was the paradox. You take a red star, collapse it, take a blue star, you can collapse it to a dot. In both cases, there's just the vacuum over here, and that radiates stuff, but it radiates the same in both cases, because it doesn't know if you have a red dot or a blue dot, and so it has no information, and then you have violated quantum mechanics. This was the puzzle, and now we have seen everything about the puzzle. What I've told you is all there is in the full technical depth of it. In string theory, we have found that the whole structure of the black hole is completely altered. The inside of the space-time doesn't even exist, so you don't actually end up getting this picture. You get actually a surface there which doesn't fall in, and now you have at least solved the information paradox. Many people thought that these small corrections might encode the issue, and we could still keep the old structure of the black hole. But using these powerful theorems of quantum information theory, we know that's not possible. We can actually prove you need a complete modification of the horizon, not a small modification, and therefore you might as well take the fuzzball solution. It is a complete modification. You needed one, you have it, even though you can't check it for all black holes and all states. It looks plausible. That's the way things should work. We had to then answer, how did the structure of the black hole change so radically? Classical physics, it seemed, should be almost good, almost perfectly good for something as big as a black hole. Why did it change so completely? And we saw the reason. Even the quantum effects are very small on any one transition of this kind from here to here. If there are many of these possible things, there's some probability to go here, some probability to go here, some probability to go here. When you add all those probabilities, the large number of these, this enormous entropy found by Bekenstein for the black hole, that large number exactly cancels the smallness of the transition probability, so you actually end up going here and not going here. Black holes are really much more quantum mechanical than you might ever have guessed. And then our final step, does the fuzzball surface actually have to behave like a firewall? Will it burn you? Well, if the real surface there, you can't really proceed any further, but falling on the surface oscillates it. These are the oscillations, and if those frequencies are the same as the frequencies of waves inside the black hole, if you fall on it hard enough to get this approximation to work for high energies, you actually can't tell the difference, so you wouldn't know that there's actually a firewall there. You'll feel you're falling through the vacuum. Well, this is my last slide over here. What next? So we have solved the information problem, but in the process, we've completely changed the structure of the black hole. Where do we go from here? And for me, the most exciting question is, we should go to solve the other big singularity we know about in physics, which is singularity at the Big Bang. Very similar. A lot of mass is being crushed down to one dot, just like happened in the black hole. A lot of mass got crushed to one dot, but in the black hole, we found that quantum effects completely changed everything. If that's going to happen here, we need a whole new theory for the Big Bang cosmology. And that's the kind of thing that we are most excited about right now. Yeah.
But the more startling implication of ADS-CFT is that it's the first concrete realization of the holographic principle. The lower dimensional CFT space is the surface of the ADS space because the field theory exists where that new dimension becomes infinite, infinitely far away. That's tough to imagine. So let's go back to our depiction of an infinite hyperbolic space from the last episode. Our universe may be infinite. In order to wrap our puny human minds around such a notion, we like to come up with boundaries. For example, we have the observable universe, that patch that we can see and beyond which light has not yet had time to reach us. Its boundary is called the particle horizon. Beyond it, there exists at a minimum thousands and possibly infinitely more regions just as large. Our observable universe is like a tiny patch of land in a vast plain. We define its horizon like we might build a little picket fence around our little patch. Meaningless from the point of view of the plain, but it makes our patch feel more homey and us less crushingly insignificant. We visited these cosmic horizons in one of the early spacetime episodes. To review, the particle horizon defines the limit of the visible past, and there's also the cosmic event horizon, defining the limit of the visible future. But these correspond to actual spherical boundaries in space, whose distances can be calculated. How mundane. There's another way to define the boundary of the universe that isn't so shy in the face of an infinite cosmos. In fact, if we twist our human intuition and our mathematics to its limit, we can build our picket fence around an infinite universe. A mathematical boundary at infinity turns out not to just be useful for doing calculations in physics, but maybe as real as the physical universe it contains. It may encode that universe as a hologram on its surface. In today's episode, we're going to talk about two ways to define this infinite boundary, and this will set us up finally for laying open the holographic principle. I promise. Let's start with a quick review of types of universe, at least the three basic types described by Einstein's general theory of relativity. The only type of non-infinite universe or closed universe is the one that curves back on itself, like the 3D analog of the 2D surface of a sphere. We call that positive curvature. Travel far enough around and you get back to where you started. Geometry is a bit broken in such a universe. For example, two parallel lines will eventually converge and cross each other. In general relativity, we call a universe with this geometry de Sitter space, after Dutch astronomer Willem de Sitter. Then there's the flat universe. Classic straightforward geometry. Parallel lines stay parallel, and it goes on forever. In GR, this is Minkowski space, after Hermann Minkowski, teacher and colleague of Albert Einstein. Finally, there's the universe with negative curvature, and the 2D analog of that is the hyperbolic surface, like an infinite saddle or Pringle. In this geometry, parallel lines actually diverge from each other. In GR, this is anti-de Sitter space because it's the opposite of the positive curvature de Sitter space. Terrible name, so we abbreviate it to ADS space. Okay, so 2 out of 3 possible universes are infinite. On the other hand, assuming all these types exist, there should be infinitely more people in infinite universes compared to people in non-infinite universes. You're probably one of the former, so let's ignore puny de Sitter space. And for today, assume we're in one of the infinite universes. How do we put bounds on infinity? This all got going in the early 60s when physicists were trying to find ways to map infinite spacetime to the edge of an infinite universe or across the event horizon of a black hole. Regular coordinates of space and time are useless there. They blow up to infinity. Physicists found mathematical ways to fuse space and time into new coordinates that suppressed the infinities. We call this process compactification. The first efforts were designed to allow physicists to cross the event horizon of black holes, at least mathematically. We have Kruskal-Zakharas coordinates, Eddington-Finkelstein coordinates, and others. But these coordinates only defeated the artificial infinity, the coordinate singularity of the event horizon, which is also something we've discussed. It was Roger Penrose who defeated the true infinity of an infinitely large universe. In the early 60s, he developed his Penrose coordinates and Penrose diagrams, also known as Penrose-Carter diagrams, for Brandt and Carter, who came up with them at around the same time. We've used them before to understand black hole event horizons, but these were originally conceived to understand the boundaries of the universe. As a quick review, start with a graph of space versus time, a space-time diagram, and then compactify. These horizontalish contours are our old time ticks, moments of constant time across the universe, while the vertical-ish lines are set locations in space in only one spatial dimension. The contours bunch up towards the boundaries so that every step on the map covers more and more space and time. The boundaries themselves represent infinite distance and infinite past and future. One amazing thing about the Penrose diagram is that the transformation preserves all internal angles. All angles between intersecting lines relative to each other stay the same. We call such a transformation conformal. And remember that word, it's going to be very, very important. This particular conformal compactification is designed to ensure that the path of every ray of light remains at 45 degrees across the map. That means only light speed paths can hope to reach these boundaries ahead, and only light speed paths can originate from these boundaries behind. Any sub-light speed paths, which means paths of anything with mass, will be swept along with the contours of space. All matter must originate at this point, representing all of space in the infinite past, and must also converge to this point, which represents all of space in the infinite future. Only light speed paths, or in the language of quantum field theory, massless fields, can access these diagonal boundaries. If we write the equations of these fields in Penrose compactified coordinates, then we can do something that seems impossible. We can track a quantum field to infinite distance and calculate its behavior there. That has a very particular use. Penrose diagrams represent a universe that is asymptotically flat. It may have some local curvature due to gravity of massive objects inside, but at its boundaries, the simple rules of non-curved Minkowski spacetime apply. That's handy because flat space is the only space where quantum mechanics is fully solvable. The most famous use of this is by Stephen Hawking, as we saw in our Hawking radiation episode. He connected a quantum field between 2 points at infinite distance, past and future, where he could define the state of the quantum vacuum in solvable flat space. Then he placed a black hole in between these points and calculated how it perturbed the balance of the quantum field traced between those points. He found that two infinitely distant regions could not both be in a perfect vacuum state if a black hole lay between them. He concluded that the black hole must generate particles, Hawking radiation, which, by the way, was a key discovery on the path to the holographic principle, as we've discussed before and which I'll review again, but not today. Today, we're just talking about boundaries, and we need a very different infinite boundary to give us our hologram. Penrose diagrams define the infinite boundary of a flat universe as a useful tool in calculation. For the holographic principle, we need the infinite boundary of a negatively curved universe, an anti-de Sitter ADS universe. Let's start with another map. Just like the Penrose diagram, we'll do a conformal transformation, all internal angles preserved, and we'll compactify layers towards the edge. But this time, we're not mapping space versus time, we'll just map 2 dimensions of hyperbolic space. In fact, let's use the most famous conformal compactification of hyperbolic space. That's right, there is a most famous conformal compactification of hyperbolic space, and you've probably seen it. This is M.C. Escher's circle limit 4, the final in a series of woodcuts inspired by a projection of the hyperbolic plane called the Poincaré or conformal disk. The basic construction is straightforward enough. Start with a circle, now fill it with a set of circle segments that all intersect the circumference at right angles. Those circle segments represent the straight lines of a hyperbolic geometry projected onto the disk. We can see the hyperbolic behavior of these arcs. They are geodesics, the straightest possible paths in this geometry. Any two paths that are parallel at one point will diverge from each other in either direction. This is a conformal transformation of a hyperbolic surface because the angles of intersection of these lines are preserved, and it's compactified because an infinite hyperbolic surface fits on a finite disk, with lengths represented by shorter and shorter arcs towards the rim. The other feature of a conformal mapping is that shapes are preserved, at least locally. We see that when we fill the circle with a regular choice of circle segments. They define a set of enclosed shapes that vary in size but not in shape. This is an example of tessellation, tiling a space with regular repeated shapes. Hyperbolic space is fascinating because there are literally infinite ways it can be tessellated with regular polygons, while spheres and flat space each only have a small finite number of possible tessellations. So, this disk can represent an infinite anti-de Sitter universe with two spatial dimensions at a single instant in time. Each tile represents the same size region of space, perhaps our observable universe. The boundary is infinitely far away and looks the same no matter where we travel. If we wanted to represent a 3D ADS universe, we could use a Poincaré ball instead. But the real power of ADS space isn't the cool art you can do with it, at least to physicists. It's the nature of that infinite boundary. Here's a mouthful. The boundary of a conformally compactified anti-de Sitter space is itself a conformally compactified Minkowski space with one fewer dimension. Got it? Cool, we're done here. Okay, let's unpack that. In fact, let's add the dimension of time to our hyperbolic projection. Stack a bunch of Poincaré disks, each representing an instant in time. They give you a cylinder representing ADS spacetime with two spatial and one temporal dimensions. Let's call that 2 + 1 dimensions. On the other hand, the surface of the cylinder has only one dimension of space, the circumference, and the same one dimension of time, 1 + 1, right? So it turns out that the surface of the cylinder, which exists only in the compactified coordinates of the interior volume, is mathematically exactly a flat Minkowski space. You can extrapolate to any number of extra dimensions, say a 3 + 1 dimensional Poincaré ball, compactify it so the infinite boundary becomes a surface. That surface is a 2 + 1 Minkowski plane. And here's the crazy thing. You can treat that surface space and the interior space, also called the bulk, as separate spacetimes with their own physics. But they are connected. Every point on that flat surface maps to a set of paths through the hyperbolic interior. Remember those circle arcs? Patterns on the surface define the structure of the interior. Represent a 2D hyperbolic plane as a compactified map, and it has an edge, at least a mathematical one. Anyone inside the hyperbolic space still has to travel infinitely far to get to that edge. Now, stack many maps to represent slices in time. The resulting column has a geometrically flat and finite surface that is a spacetime all on its own. The rules of interactions between cells on that surface is a quantum field theory, but those rules translate to interactions in the volume, in the bulk, where it's a theory of gravity. ADS CFT is a hint that we may live in a holographic universe.
So in cosmology, we can describe this in terms of Hubble's law, which tells you indeed that the velocity goes with the distance, and the constant in front we call Hubble's constant. And so the distance where this velocity is equal to the speed of light is called the horizon distance, and that's measured in terms of this constant h. Now, why do I talk about this horizon? This horizon has very much the same properties as black hole horizons. And I told you horizons have information. So we can use here sort of an holographic idea of how much information can be put inside our universe. So if we would think about our universe as a very large computer where we store a lot of information, how much can there be in there? Well, not more than the horizon of this area, the area of the horizon. And that actually tells you exactly how much information is contained in the universe.
Before I give you a summary of all quantum mechanics, I'm going to give you a 90-second history of it so you can get a little background on how quantum mechanics came to be. So here we go. Classical mechanics failed to describe how an electron could orbit an atom. An accelerating charge like that of an electron around a nucleus always creates electromagnetic radiation according to Maxwell's classical equations. This means the electron would constantly lose energy and eventually crash into the nucleus. Niels Bohr solved this problem by hypothesizing that electrons could exist without radiating energy if they rotated in quantized orbits proportional to Planck's constant. Louis de Broglie later showed that if such quantized orbits exist, then electrons must be waves. Astonishingly, experiments showed that not only electrons but all quantum particles like photons and even atoms exhibit interference, with no exceptions, implying everything else must be waves too. Erwin Schrödinger developed an equation to explain this wave-like behavior. His equation describes how a wave evolves over time. But the problem is that whenever we detect these quantum objects, we detect them as particles, not as waves. This presents a conundrum. Experiments like the double-slit experiment suggest waves, but detection appears to indicate particles. So Max Born came up with the idea that we should interpret the wave determined by the Schrödinger equation as a kind of probability. This allows a single quantum object to be described as a wave. So we've adopted a wave interpretation of a particle, which evolves through time according to the Schrödinger equation. And analogous to a classical wave, it does not have a distinct location. It has only a probability of being found at any particular location. This location can only be determined once we measure it, not in advance. So that's your 90-second summary. So now that you know a little bit about the history of quantum mechanics, let me explain what the big deal is. It would be nice if we could just scale down everything we know about our macro world to the quantum world. For example, if the Newtonian mechanics of a basketball applied to electrons and atoms, there would be no problem. Everything would be intuitive, and we could relate everything to our everyday experience. But the universe didn't make things so simple for us. Quantum objects such as electrons, photons, and atoms are not like little basketballs or tiny pieces of dust. They're like waves. because they create interference patterns, like we see in the double-slit experiment. The Schrödinger equation was developed to explain how these waves evolve, and it's quite accurate. So if we have a rigorous mathematical model to describe these waves, what's the big deal, since we know how it works? The problem is that we only observe particles, or at least particle-like behavior, whenever we detect these quantum objects. This phenomenon can be seen in places like a cloud chamber and particle accelerators. The subatomic objects seem to behave like particles, not waves. So to incorporate this into our quantum mechanics theory, the concept of measurement was introduced. So you'll hear physicists say, at least in the most common interpretation of quantum mechanics, that whenever a measurement is made, the wave collapses and becomes a very localized wave, which effectively makes it look and behave like a particle. Measurement means an interaction of the quantum object with some kind of measuring device. More specifically, an irreversible exchange of energy somewhere in the measurement process. This seems nice and clean, but there's a huge problem. No one can explain how or why this wave collapse occurs through measurement. This is called the measurement problem in quantum mechanics. And since all our information comes from a measurement of some kind, we can never directly see or touch this quantum world. Everything we observe must go through this measuring process that seems to result in the conversion of quantum objects into particles, like the classical world we are familiar with. So, how this wave evolves according to the Schrödinger equation, while it's highly accurate in making predictions, is never actually seen. Like I showed 2 videos ago, ultimately quantum theory boils down to a theory of interacting harmonic oscillators, combined with a measurement postulate. But no one can explain how the interactions of the harmonic oscillators are different than the interaction of the measurement device. If we really want to understand reality, this is a fundamental problem that we need to resolve. Now, having said all this, let me add that not resolving the measurement problem has not prevented us from predicting and measuring outcomes from these equations. There is a philosophy called just shut up and calculate, meaning don't worry about what's really going on. If the bottom line is that all our equations work and are highly accurate, that's all we should care about. I don't subscribe to this kind of thinking myself because I think that the purpose of scientists, particularly physicists, is to explain the inner workings of the universe, not simply create equations that make predictions without a deep understanding. In classical mechanics, things are concrete. Objects have distinct positions and velocities. In quantum mechanics, objects have wave-like behavior. They're more specifically described by wave functions, which are abstract mathematical solutions to the Schrödinger equation. These waves aren't localized, but instead take up all of space. It isn't until you look for a particle that it becomes what appears to be a particle. Before that, the particle is a collection of probability waves that theoretically extend out to the entire universe. Now, this has some pretty profound consequences. One is called the uncertainty principle, which states that you can never simultaneously know exactly where something is and how fast it's going. More precisely, we cannot know the position and momentum at the same time. This has to do with the probabilistic nature of quantum mechanics. Let's do an example to understand why this is the case. When we say we can't know where an electron is because it's a wave, what we mean by wave is the wave function from the Schrödinger equation. And this is related to the probability of finding the electron at any point in space. But a perfect sine wave for the electron spreads that probability throughout all of space. So the position of the electron is completely uncertain. But a perfect sine wave means we know it's the wavelength. So we would know its momentum quite precisely because of the de Broglie relation, where momentum equals Planck's constant over the wavelength. So in this case, we have an infinite uncertainty in position, but no uncertainty in momentum. On the other hand, if we want to know the position of the electron precisely, we would need to add many waves of different wavelengths so that we can get an interference pattern such that we get a more localized wave. This localized wave would give us a more precise location, but now we have no idea what the momentum is. This is because all the waves that are needed to create the localization, being that they are of different wavelengths, have different momentums, using the same de Broglie relation. So either we know the position very precisely or the momentum precisely, but not both. What's important to understand is that this is not a limit of our measuring equipment. It's that exact answers to both the momentum and the position of a quantum object do not exist in the universe at the same time. The universe itself doesn't know the answer. Now, this is hard to accept and goes completely against our everyday experience. So you have to ask, why don't we see this wave behavior in macro objects, like a basketball or tennis ball or even a tiny particle of dust? Well, I'll let you in on a little secret. Dust particles, tennis balls, and basketballs do propagate as waves, just like electrons. In fact, everything does. And their wavelengths can be calculated just like a photon or electrons using de Broglie's formula. Wavelength equals Planck's constant divided by momentum. But for large objects, the momentum is so much bigger than the Planck's constant that their wavelengths are an undetectable fraction of their physical size. So we can never notice their quantum mechanical properties. For example, the wavelength of something the size of a tennis ball moving 10 meters per second is 10 to the negative 33 meters. This is less than the width of a proton, so we would never notice it. A second consequence of wave-like behavior is non-locality. A wave exists over multiple regions of space. This non-locality explains interference, but it also means that waves can add together to give complex interference patterns. So waves of multiple particles can add together to give a single wave function corresponding to multiple particles. This gives rise to a strange correlation between such particles in a phenomenon called entanglement. Einstein called this spooky action at a distance because it appears to indicate instant communication between distant objects at faster than the speed of light, which is forbidden by relativity theory. But while two or more objects are correlated, no communication is actually happening. Correlation does not mean communication. The wave behavior of electrons also means that the concept of circular orbits of electrons around the nucleus of atoms that you commonly see everywhere when an atom is depicted is wrong. A better picture is that they exist in a well-defined probability cloud around the nucleus that might look more like this. The main point is that the universe is quantized. Familiar quantities such as energy, momentum, electric charge, mass, and possibly even time and space are not continuous. They occur in discrete quantum units. So for example, the state of an electron is quantized. By state, I mean its energy, angular momentum, and other properties. So an electron in a state of 3.4 electron volts of energy that moves to 13.6 electron volts of energy does not pass through any intervening energy values. It just disappears from its old state and reappears in the new state. It never exists between these two states. This is how an electron moves from a lower energy shell of an atom to a higher energy shell. This quantization is not directly observable in our daily experience because the intervals between the units are too small for us to notice. It isn't that quantum mechanics only exists at small scales. Quantum mechanics is all there is. It is everything. Newtonian mechanics, or the physics of our macro scales, just happens to be a good approximation of the underlying, more fundamental quantum mechanical universe.
Now you might think this is a great model. We know everything now. We can stop here. But we can't, because quantum mechanics has some problems too. There are some things it cannot explain, and we get the wrong results, just like when we tried to explain the electron's orbit with the classical formulation. First of all, quantum mechanics is not relativistic. That is, it will give you wrong results if the quantum object is moving close to the speed of light. Schrödinger's equation simply doesn't obey Einstein's theory of special relativity. The practical result of this is that it doesn't incorporate a speed limit, the speed of light, needed to make causality work. For example, it allows for two measurements to influence each other faster than light. This would mean that there would be some reference frame in which the future could influence the past, breaking causality. A second problem with quantum mechanics is that it only tells you how a particle evolves over time. That is, how it goes about its business. It does not tell you how it is created or annihilated. So it can't account for things like beta decay due to the weak nuclear force, where a neutron transforms into a proton, an electron, and an antineutrino. In this case, quantum mechanics breaks down because it doesn't work if we change the number of particles. In the case of the beta decay I just described, the down quark of a neutron decays into an up quark, changing the neutron to a proton, and at the same time emits an electron and an antineutrino with a mediating W boson. This change to other particles can't be described by quantum mechanics. This is where quantum field theory explains things that quantum mechanics cannot explain on its own. So, what is quantum field theory? Well, it's a mathematical framework that combines classical field theory. A classical field would be like a magnetic field as described by James Clerk Maxwell, special relativity, and quantum mechanics. There is a field for every particle of the Standard Model. So in our beta decay example, there would be a field for the down quark, the W boson, the up quark, the electron, and the antineutrino. All these fields extend out in all of space-time. In other words, the fields are always there and exist everywhere, including inside your body. Now, although they exist everywhere and you can't see them, they are not nothing. They are teeming with virtual particles. These are particle-antiparticle pairs that get created and destroyed. So for example, the down quark field will always have some spontaneous creation of down quarks and anti-down quarks, which get created and annihilated almost instantly. They come in and out of existence constantly. These virtual particles can't be measured, but nature allows the creation of these virtual particles by letting them borrow energy from the vacuum, as long as that energy is put right back into the vacuum. This happens so quickly that it's as if nature doesn't register them as real measurable particles. We can visualize these fields as a kind of ocean. Just like the ocean wave has some turbulence, the fields always have a kind of turbulence, even in their ground state of minimal energy. This turbulence is due to the virtual particle creation and annihilation I just described. In these turbulent seas, if there's enough energy, a large wave can be created, which can be measured. These are the real particles. So in the up quark field, for example, an up quark will be created if there's energy of 2.3 mega electron volts, or MeV, which is the mass of one up quark. Two quarks will be created if there's energy of 4.6 MeV. So a particle is nothing more than an excitation in this field. These excitations are quantized, not continuous. So the fields can only create particles in integer increments. They cannot, for example, have 1.5 up quarks, only 2 quarks or 3 quarks, etc. Now energy can be transferred between two fields via a mediating boson field. This is considered an interaction or a force. Matter particles can't interact on their own without a mediating boson. So while in quantum mechanics there's no way for the neutron to split its energy into 3 different particles, a proton, electron, and an antineutrino, in quantum field theory this can be done via energy exchange between the fields. You start with the fields of all the different particles, which are always there, and you finish with the fields of the same particles. Some of them just have more or less energy after the exchanges of energies, depending on the interaction. So in our beta decay, for example, you start with the down quark field. This field transfers its energy to the up quark field and the W boson field. The W boson field then transfers its energy almost immediately to the electron field and the antineutrino field. So we started with 1 particle in the down quark field and we ended up with 3 particles simply by the fields exchanging energy. Note that although the number of particles changed, the total energy is always conserved. If you add up all the masses and kinetic energy at the beginning, they will add up to all the masses and kinetic energy at the end. In other words, the energy of the fields is the same before and after the energy exchange. So by having quantum fields, we can mathematically account for and model creation and annihilation of particles, as well as the mechanism of force exchange. The icing on the cake is that the theory is fully relativistic, meaning it's free of causality violations. But even this modification of quantum mechanics is not perfect. For example, it's still missing gravity. We do not have a quantum field theory for gravity. If we did, it would mean that we could model a field for the theoretical graviton particles, and gravity would be mediated between matter particles by the exchange of this graviton boson. So even QFT, which is extremely accurate for the forces and particles we do know about in the standard model, remains as yet incomplete. The fact that we don't have this tells us something. It reminds me of the saying that when you have a hammer as your tool, everything looks like a nail. Our tool is QFT. So far, everything we know has been a nail. So either gravity is not a nail, or maybe we just don't really know how to use the hammer. But still, in my view, QFT is probably the most beautiful theory in science, and here's why. Because it tells us that the universe and everything in it, including us and all living things, the whole planet, every star, every galaxy, and even things outside the visible universe, are all connected. Everything, even our thoughts, dreams, and ideas, are composed of excitations in the same quantum fields. And all these fields extend to not only all of space, but all of time. The universe is made of the same basic stuff, and we are all simply a series of excitations in it. So when someone says we're all one, or that we are all connected to the universe, this is not just a fanciful idea, but has a real physical meaning. I find this to be beautiful.
This is a simulation of the vacuum on its own, what we normally think of as empty space.
Empty space is actually full of these quark and gluon field fluctuations. And on average, it is possible to annihilate a quark from empty space because it's not empty.
That just sounds like the most ridiculous idea, that you're meant to have empty space and yet you can go and get rid of stuff from it.
That's right. So it isn't empty.
Now it seems counterintuitive that the vacuum at its lowest energy state should contain all of this stuff. But in fact, to clear out the fluctuations and create a truly empty vacuum would require a lot of energy.
The empty vacuum actually costs an enormous amount of energy to create. And if you were able to create it, you'd discover that that is actually unstable, that any sort of perturbation would push that empty vacuum into something where the vacuum is actually full of quantum field fluctuations.
Imagine I have a beautiful tree that's filled with oranges. And I ask myself, what is the orange made of? How do I answer that question? Well, I want to look deeply inside the orange, so I magnify it. And I magnify it again, and if I keep on doing it, deep inside, sooner or later I begin to see molecules come into view. But molecules are not the end of the story, because the molecules, I can enlarge them. And if I make them big enough deep inside, I begin to see atoms. Atoms are not the end of the story too, because we have electrons zooming around the nucleus. Deep inside, mostly empty space in the atom, but deep inside, we see the nucleus. So if I grab that and magnify it, I see that the nucleus is itself made of particles, neutrons and protons. And if I grab one of the neutrons and magnify it, I find yet further particles, little tiny quarks inside. Now that is where the conventional ideas stop. String theory comes along and suggests that inside these particles there is something else. So if I take a little quark and I magnify it, conventional idea says there's nothing inside, but string theory says I'll find a little tiny filament, a little filament of energy, a little string-like filament. And just like the string on a violin, I pluck it and it vibrates, creates a little musical note that I can hear. The little strings in string theory, when they vibrate, they don't produce musical notes, they produce the particles themselves. So a quark is nothing but a string vibrating in one pattern. An electron is nothing but a string vibrating in a different pattern. A neutrino, nothing but a string vibrating in a different pattern still. So if I take all of this back together, I have my ordinary orange, and if these ideas are right, they are speculative, but if they are right, deep inside the orange or any other piece of matter is nothing but a dancing, vibrating cosmic symphony of strings. That's the basic idea of string theory.
Well, when string theory came along, people studied its mathematics and in short order recognized that the equations of string theory were inconsistent in a world that only has 3 dimensions of space. And some very insightful theoreticians said, well, what happens to these equations if there aren't just 3 dimensions of space? And they found through their manipulations, mathematical manipulations, that if the world had 9 dimensions of space, not 3 dimensions of space, then all of a sudden the previous mathematical problems, they evaporated. Now what do you do with that? Well, one approach is to say, well, fine, that's a mathematical result. If there are 9 dimensions, the math works, so what? Our world clearly doesn't have 9 dimensions. But some took the lead that echoed back from the observations of Kaluza and Klein and said, well, maybe there really are additional dimensions of space. Just as Kaluza and Klein said, they're all around us, they're just too small, we haven't seen them. Therefore, maybe this idea of string theory, that there are extra dimensions, maybe that's real. Maybe they're all around us.
The presence of these additional dimensions also allows a much more varied range of vibrational modes, and therefore a greater diversity of potential types of particles. In addition, there are a multitude of different ways to curl up 6 dimensions, and each possibility will predict a different universe, where the strings can adopt different vibrational modes and therefore behave like different particles. By carefully choosing the way in which these 6 dimensions are compactified, we can adjust our description so that it predicts the same particles as those we observe in our world. That said, among the myriad of possibilities, it is not yet clear why our universe would contain the particles of the standard model rather than some other possibility. According to some still speculative hypotheses, the geometry of the universe might even have varied over time, transitioning from one compactification to another, and the laws of physics could thus have changed during the first instance of our universe.
And this is one of the most famous one in particular. In a paper by Juan Maldacena in 1997, he proposed 3 different classes of such holographic dualities in different dimensions, and one of which relates n equal to 4 Zucchius-Mills theory. So this is a very particular quantum field theory, which I will discuss later on, in 3+1 dimension Minkowski spacetime. So to string theory in 5-dimensional anti-de Sitter spacetime. And yes, I should be precise there. So this is string theory, not precisely in anti-de Sitter spacetime, because string theory, of course, is only well-defined, in particular fermionic string theory, type 2 string theory is only well-defined in 10 space-time dimensions. So, which means, of course, that you need a geometry whose dimension add up to 10. So this is more precisely ADS5 times S5. S5 is a 5-sphere, and ADS5 is this negatively curved anti-de Sitter spacetime. And moreover, it is not string theory just in anti-de Sitter spacetime, but the anti-de Sitter spacetime can be, of course, deformed. So it's only asymptotically anti-de Sitter spacetime. And so this is one of the famous relations between a quantum field theory on the one hand side, where there are no gravitation degrees of freedom, to string theory, and we know the massless degrees of freedom here are, among other degrees of freedom, the graviton. So this conjecture says that we should be able to map local gauge invariant operators in this Superhang-Mills theory, which I call now O of x, to fields on the gravity side. And those fields, of course, depend on x, like the coordinates of our Minkowski spacetime, on this additional scales and on this additional coordinate set of our asymptotically anti-de Sitter spacetime. So this is basically mapping the degrees of freedom, like operators and fields. But of course, in addition to that, I also have to map the dynamics. In terms of the quantum field theory, the dynamics is encoded what we call generating functional. Usually, if you learn quantum field theory the first time, you encounter this generating function set of J. Here I call the source not J, but phi 0. And this is just this expression e to the minus integral d4x phi 0 of O of x, which means if you take functional derivatives of phi 0 of x, and then set at the end phi 0 of x to 0, you compute endpoint correlation functions of those local gauge invariant operators O. So this is why this generating functional set CFT contains basically the dynamics of your quantum field theory. It contains all the endpoint correlation functions of local gauge invariant observables. On the other hand side, we have string theory, and in terms of a kind of a string field theory, we can think of having here a partition function, set string, where the fields phi on the string theory, so the string theory lives in ADS5, or asymptotically ADS5, and asymptotically ADS5 has a boundary, a conformal boundary. And at the conformal boundary, these fields phi, they should take these values phi 0, which are precisely the sources in my dual quantum field theory. I have to admit that, of course, first, this equal sign is a bit ambitious, because this is a conjecture, but both sides are very tricky to define. So how does this partition function in string theory look like? So far we don't know. We only know it for very particular cases, which I will comment on later. And also in a non-interacting, strongly interacting quantum field theory, defining or computing this partition function for all the endpoint correlation functions is, of course, a very difficult and demanding thing to do.
Babies may suck at math, but they're actually surprisingly good at quantum mechanics. Well, one fundamental aspect of it anyway. The peekaboo game is thought to be so hilarious to babies because they lack object permanence. Hide your face with your hands and a baby won't automatically assume that you kept existing. Reveal your face again and it's as though you popped into existence from nothing, which is of course a hilarious thing to do. Kids get over this pretty quickly as they learn that things don't magically pop into and out of existence for no reason. By the time they grow up and go to college to study physics, the notion of object permanence is so deeply embedded that we don't even bother teaching it in Physics 101. And yet the idea that the universe keeps existing when we're not looking at it is a pretty fundamental implied assumption behind all of classical physics. Indeed, most of science takes it for granted that the universe is real whether or not we're looking at it. This notion that the universe exists independent of the mind of the observer is called realism in physics. But quantum mechanics is so bizarre that it still has scientists wondering if we need to reject even this basic premise. This was the source of one of the most heated debates at the advent of quantum mechanics. On the one hand, Niels Bohr insisted that it was meaningless to assign reality to the universe in the absence of observation. In the intervals between measurement, quantum systems truly exist as a fuzzy mixture of all possible properties, what we call a superposition of states. In between observations, the wave function describing this superposition is a complete description of reality, and our experience of a well-defined material universe only has meaning at the moment of measurement. This peekaboo universe is the heart of Bohr's Copenhagen interpretation. On the other hand, Albert Einstein insisted on an objective reality, a reality independent of our observation of it. He insisted that the wave function, and by extension quantum mechanics, is incomplete. There must exist what we call hidden variables that reflect a more physical underlying reality. In an effort to demonstrate the silliness of Bohr's idea, Einstein, along with Boris Podolsky and Nathan Rosen, proposed a quantum scenario that showed that in order to abandon the assumption of realism, you also had to abandon a concept almost as sacred: locality. Locality is the idea that each bit of the universe only acts on its immediate surroundings. This is fundamental to Einstein's relativity, which tells us that the chain of cause and effect can't propagate any faster than the speed of light. The Einstein-Podolsky-Rosen, or EPR paradox, introduces one of the most mysterious ideas in quantum mechanics: quantum entanglement. Here's the idea. Two particles interact briefly, they influence each other so that their properties are somehow connected, and yet we refrain from measuring these properties to preserve quantum uncertainty. Quantum mechanics requires that we describe the particle pair with a single combined wave function that encompasses all possible states for both particles. We call such particles an entangled pair. Now, according to the Copenhagen interpretation, any measurement of one particle automatically collapses the entire entangled wave function and so affects the results of measurements of the other particle. That's an influence that could, theoretically, be transmitted instantly across any distance, and even back in time, violating locality and possibly violating causality. Einstein et al. Thought this was very silly. They thought that every spatial point in the universe must be real and physical and defined by knowable quantities, local hidden variables, that could affect each other no faster than the speed of light. The argument between Bohr and Einstein felt a bit philosophical at the time, but in 1964, Irish physicist John Stuart Bell proposed an experiment to resolve the debate. It involves entangled electron and positron pairs. When spontaneously created from a photon, these particles will always be spinning in opposite directions to each other. However, until measured, we can't know which direction either is spinning. We just know that they're opposite each other. Their wave functions are therefore entangled. Measurement of the spin of one of these particles tells us the spin of the other, no matter how large the distance between them. But in quantum mechanics, measurement actually affects the thing you're measuring. In the case of quantum spin, that measurement effect is especially weird. We define spin direction according to the spin axis. That axis can point in any direction. But to measure spin direction, we need to choose an axis to align our measuring device. We always find that the observed quantum spin aligns itself with our chosen measurement axis. If we choose to measure vertically, the spin will turn out to be up or down. If we measure horizontally, it'll be left or right. Measurement forces the alignment of the measured particle. But how does this affect the spin of its entangled partner? The answer would settle the Bohr-Einstein debate. Let me explain. Scenario 1, if Einstein was right. Imagine the response of each particle to all possible spin measurements is encoded in each particle at the moment of their creation, as hidden variables local to each particle. Nothing we do later to one particle will then affect the other. When we later measure the spins of both particles, there will be a correlation in the results because the particles were once connected, but there'll be no correlation due to our choice of measurement axis. Scenario 2. Bohr was right. What if, between creation and measurement, the electron and positron only exist as a wave function of all possible states? In that case, measurement of one particle's spin should cause the entire wave function to collapse, to take on defined values. Both particles should then manifest opposite spins along whichever axis we choose for one of the particles. That should lead to a correlation between our choice of measurement axis for the first particle and the spin direction then measured for the second. This is exactly the spooky action at a distance that made Einstein so uncomfortable. So John Stuart Bell figured out a set of observable results, the so-called Bell inequalities, that we'd expect to see in the case that Einstein was right and quantum mechanics needs local hidden variables. But if an entanglement experiment violates the Bell inequalities, then local realism is also violated. By the way, Veritasium describes this experiment in much more detail in this video. I recommend you check it out. It's a tricky experiment because entangled quantum states are hard to produce, but even harder to sustain. Any interaction can destroy the entanglement. But in the early 80s, French physicist Alain Aspect succeeded. Instead of looking at the entangled spins of an electron-positron pair, he used photon pairs with entangled polarizations. Polarization is just the alignment of a photon's electric and magnetic fields. But the principle is the same, and Aspect found that there was a correlation between the choice of polarization measurement axis for one photon and the final polarization direction of its entangled partner. The Bell inequalities were violated. The experiment was even set up so that the influence had to travel between the photons at faster than the speed of light. Since then, many experiments have verified this result over larger and larger distances. The instantaneous influence has been observed over many kilometers at this point. The delayed choice quantum eraser, which we already covered, is yet another example of this strange result. It's now been thoroughly confirmed that the Bell inequalities are violated, suggesting that the wave function cannot have local hidden variables. So does this confirm the Copenhagen interpretation and kill both locality and realism? Do we live in a peekaboo universe that vanishes into quantum abstraction when we aren't looking at it? Are babies really better at quantum mechanics than Einstein? Well, not so fast. The results of these entanglement experiments do seem to violate local realism, but that may mean a violation of realism or just of locality. In fact, it was Dr. Bell's opinion that the violation of his inequalities disproved only locality. Realism could be salvaged. Non-locality requires that entangled particles affect each other instantaneously. That sounds blasphemous to anyone who accepts Einstein's theory of relativity. However, non-locality and relativity can actually be perfectly consistent. Relativity requires that causality is preserved, so no faster than light information flow. But none of these entanglement experiments allow any real information to be transmitted between particles. It's only possible to see the influence between the entangled partners after measurements have been made and those measurements are compared. Just as we saw with the delayed choice quantum eraser, the universe seems to conspire to avoid the paradox of information traveling faster than light or backwards in time. The Copenhagen interpretation remains consistent with all quantum observations. Niels Bohr's peekaboo universe may be the universe we live in. However, realist and hidden variable interpretations are also consistent as long as they abandon locality. For example, entangled particles may be dimensionally connected by Einstein-Rosen bridges, wormholes that allow instantaneous contact even between great spatial separations. Also, the de Broglie-Bohm pilot wave theory works by assuming realism and non-local hidden variables. Misinterpretation of the ideas of quantum mechanics has spawned some of the worst quackery pseudoscience, hoo-ha, and unfounded mystical storytelling of any scientific theory. It's easy to see why. There are some pretty out there explanations for the processes at work behind the incredibly successful mathematics of quantum mechanics. These explanations claim stuff like things are both waves and particles at the same time. The act of observation defines reality. Cats are both alive and dead. Or even that the universe is constantly splitting into infinite alternate realities. The weird results of quantum experiments seem to demand weird explanations of the nature of reality. But there is one interpretation of quantum mechanics that remains comfortably, almost stodgily, physical. That's de Broglie-Bohm pilot wave theory. Pilot wave theory, also known as Bohmian mechanics, stands in striking contrast to the much more mainstream ideas of, for example, the Copenhagen and many worlds interpretations. Now, we've covered both of those before, and those episodes are really worth a look. Pilot wave theory is perhaps the most solidly physical, even mundane, of the complete and self-consistent interpretations of quantum mechanics. But at the same time, it's considered one of the least orthodox. Why so? Because orthodoxy equals radicalism plus time. And the founding fathers of the Copenhagen interpretation of quantum mechanics, Niels Bohr and Werner Heisenberg, were radicals. When quantum theory was coming together in the 20s, they were fervent about the need to reject all classical thinking in interpreting the strange results of early quantum experiments. One aspect of that radical thinking was that the wave function is not a wave in anything physical, but an abstract distribution of probabilities. Bohr and Heisenberg insisted that in the absence of measurement, the unobserved universe is only a suite of possibilities of the various states it could take were a measurement to be made. And that upon measurement, fundamental randomness determines the properties of, say, the particle that would emerge from its wave function. This required an almost mystical duality between the wave and particle-like nature of matter. Not everyone was so sure. Einstein famously hated the idea of fundamental randomness. But to counter Bohr and Heisenberg, there needed to be a full theory that described how a quantum object could show both wave and particle-like behavior at the same time without being fundamentally probabilistic. That theory came from Louis de Broglie, the guy who originally proposed the idea that matter could be described as waves right at the beginning of the quantum revolution. De Broglie's theory reasoned that there was no need for quantum objects to transition in a mystical way between non-real waves and real particles. Why not just have real waves that push around real particles? This is pilot wave theory. In it, the wave function describes a real wave of some stuff. This wave guides the motion of a real point-like particle that has a definite location at all times. Importantly, the wave function in pilot wave theory evolves exactly according to the Schrödinger equation. That's the equation at the heart of all quantum mechanics that tells the wave function how to change across space and time. This means that pilot wave theory makes the same basic predictions as any other breed of quantum mechanics. For example, this guiding wave does all the usual wavy stuff, like form an interference pattern when it passes through a pair of slits. Because particles follow the paths etched out by the wave, it'll end up landing according to that pattern. The wave defines a set of possible trajectories, and the particle takes one of those trajectories. But the choice of path isn't random. If you know the exact particle position and velocity at any point, you could figure out its entire future trajectory. Apparent randomness arises because we can't ever have a perfect measurement of initial position, velocity, or other properties. But this hypothetical predictability means that a pilot wave universe is completely deterministic. When de Broglie presented his still incomplete theory at the famous Solvay conference of 1927, it didn't go down so well. Technical objections were raised, and Niels Bohr doubled down on the probabilistic interpretation. De Broglie was convinced, and he dropped pilot waves altogether. The idea was forgotten for decades, and Copenhagen became the orthodoxy. It took until 1952 for another physicist, David Bohm, to feel very uncomfortable with some of the wackiness of Copenhagen and to rediscover de Broglie's old idea. Bohm took up where de Broglie left off and completed the theory. The result was Bohmian mechanics, also known as de Broglie-Bohm pilot wave theory. These days, more and more serious physicists are favouring Bohm's ideas. However, it's far from being broadly accepted. De Broglie himself remained firmly in the Copenhagen camp even after Bohm's efforts. See, although pilot wave theory makes all of the usual predictions of quantum mechanics, it has some really fundamental differences. Those differences are in the sort of special thinking you need to do in order to accept pilot waves over other interpretations. In fact, most of the arguments for or against it are about this special thinking. Are you more or less comfortable with the oddness of pilot waves versus the oddness, say, of Copenhagen or many worlds? So what uncomfortable thinking does pilot wave theory require? Well, for one thing, it needs a teensy bit of extra math that mainstream interpretations don't. As well as the Schrödinger equation that tells the wave function how to change, it also has a guiding equation that tells the particle how to move within that wave function. That extra math is considered unparsimonious to some, a needless added complexity. However, the guiding equation is derived directly from the wave function, so some would argue that it was there all along. A more troubling requirement of Bohmian mechanics is that it does contain real complexity that is not encoded in the wave function. That's something that Niels Bohr was so fervently against. Bohmian mechanics has so-called hidden variables, details about the state of the particle that are not described by the wave function. According to pilot wave theory, the wave function just describes the possible distribution of those variables given our lack of perfect knowledge. But hidden variables have a bad rap in quantum mechanics. Pretty soon after de Broglie first proposed pilot waves, the revered mathematician John von Neumann published a proof showing that hidden variable explanations for the wave function just couldn't work. That proclamation contributed to the long shelving of pilot wave theory. But in fact, von Neumann didn't quite get the full answer. It turns out that the restriction against hidden variables only applies to local hidden variables. So there can't be extra information about a specific region of the wave function that the rest of the wave function doesn't know. This was figured out pretty soon after von Neumann's paper by German mathematician Grete Hermann, although her refutation wasn't noticed until it was rederived by John Bell in the 1960s. This helped the resuscitation of pilot wave theory because Bohmian mechanics doesn't use local hidden variables. Its hidden variables are global. The entire wave function knows the location, velocity, and spin of each particle. Bohmian mechanics doesn't use local hidden variables. Its hidden variables are global. The entire wave function knows the location, velocity, and spin of each particle. This non-locality is another weird thing you have to believe in order to accept pilot waves. Not only does the entire wave function know the properties of the particle, but the entire wave function can be affected instantaneously. So a measurement at one point in the wave function will affect its shape elsewhere. This can therefore affect the trajectories and properties of particles carried by that wave, potentially very far away. But quantum entanglement experiments show that this sort of spooky action at a distance is a very real phenomenon. Again, we've gone into the non-locality of entangled particles in detail before, also worth a look. It's a tough idea to swallow, but experiments indicate that some type of non-locality is real, whether or not we accept pilot waves.
So turbulence it is a very, very different kettle of fish. It's a very different area of physics. And everything you want to know about turbulence is contained in this equation. So this is one of the great equations of theoretical physics. There are really two preeminent equations of classical physics. One is Einstein's equations of general relativity that describe gravity, and the other one is this. This is the Navier-Stokes equation, and it describes fluids. I should just say, what's a fluid? A fluid is anything that's a liquid or a gas, roughly speaking. So anything that's a liquid or a gas, the way it moves is described by this equation here. It's got a variable u. U is the velocity of the fluid. And so this equation tells you how the velocity of the fluid changes over time. Okay? It's a very important equation. It's also a very old equation. So the first three terms here were written down over 250 years ago. This last term is much more recent. This last term was written down 201 years ago. It was first written down by Navier. Navier was, I only learned this recently. Navier was a French engineer. But he was a French engineer that loved mathematics much more than he loved engineering, which turns out to be perhaps not the best thing to do if you're an engineer. So he rose in the ranks of engineering in France, and he became the chief bridge builder in France. And he was tasked with building France's best ever bridge, some fancy suspension bridge over the Seine, right in the middle of Paris. In fact, he boasted it was going to be for the glory of France, the greatest bridge ever built. He also boasted that he was using the latest in modern mathematics, where the latest in modern mathematics meant Fourier analysis. You might be seeing where this story is going. It turns out that Fourier analysis is really no substitute for concrete. He took 2 years to build the bridge, and 2 weeks before it was first to open, the first cracks showed in the bridge, and it was torn down before anyone ever crossed it. So that's Navier's legacy. But in addition, in his spare time, he made one of the great contributions to physics, which is he wrote down this term here. So what is this equation? This equation is basically F equals ma for a fluid. The terms on the left is the acceleration of the fluid, and the terms on the right are two forces. This is the force due to pressure. This capital P here is pressure. And this is a force due to some friction as one piece of the fluid rubs against the other. It's called the viscosity term. This nu here is viscosity. So it's a reasonably simple equation. It's a version of F equals ma. By the way, you might be wondering what Stokes is doing. I'm not quite sure why Stokes is there. Stokes was the 5th person to write down this term. So it's not quite clear to me why Stokes gets his name on this equation, but okay, it's called the Navier-Stokes equation. Why is it important? It's important because in certain regimes, this equation describes everything in the universe. And I mean that literally. Take anything at all, any substance, and throw it in a box, throw a bunch of it in a box, and heat that stuff up until it melts. And it doesn't matter what you started with, the stuff in the box will move, and the way it moves will be described by this equation here. Okay? So for example, there are, 100 and so elements in the periodic table. You can take an inert gas, or you can take one of the alkaline earth metals. If you throw them in the box and you make sure they're in the liquid or the gas phase, both of those substances, no matter what you started with, are going to be described by this equation. Okay? It's a remarkable statement. You know, if you're doing an undergraduate degree in physics, that's 4 years of your life learning about all the different things in the universe and all the different properties. But in a certain regime, all of those differences disappear. Everything acts in the same way. In fact, it's even more impressive than I've said. You can take very exotic substances. So about 20 years ago, physicists succeeded in making protons and neutrons melt. So what does that mean? That this flux tube between quarks, if you heat it up to a high enough temperatures, and I don't know what those temperatures are, like a gazillion Kelvin or something, but if you heat it up to high enough temperatures, that flux tube melts. And when the flux tube melts, the quarks are actually free to roam around. So 20 years ago, experimenters succeeded for the first time in 13 billion years in freeing quarks from their prison of protons and neutrons, and they formed a new state of matter called the quark-gluon plasma, in which quarks were roaming around freely in some hot environment. The quark-gluon plasma lasted a fraction of a second, but in that fraction of a second it moved, and the way it moved was described by this equation here, okay, with some relativistic embellishments, but basically this equation here. So it's an astonishing equation. Actually, there's one more thing I'll tell you. One of Stephen Hawking's great discoveries is that black holes are hot. If you take a black hole, it emits heat. Not very hot, but nonetheless, it emits heat. So, said another way, you can think of a black hole as a way to heat up space and time, whatever that means. Black hole is a way to heat up space and time. So some years ago, physicists, most of them here in India, led by Shiraz Minwala and others in TIFR, understood that the event horizon of a black hole should be thought of as some fluid-like substance. And if you drop something into a black hole, the event horizon ripples, and they showed that the way the event horizon ripples is governed by this equation here. So it's utterly remarkable, and this equation really describes everything in the universe, and it's important that we understand it for that reason. All right, so what's the setting? There are some things about this equation we understand beautifully. You can take courses on fluid mechanics in your undergraduate degree. I urge you to do so. It's a gorgeous subject. But there are many things about this equation that we do not understand. Here is a question that we don't understand about this equation. It's an unbelievably simple question. You take a pipe and you make water flow through the pipe, and you want to ask how much pressure should I force on the end of the pipe to make the water flow? It's hard to think of a simpler question than that about fluids. We don't know the answer to that question. That's how hard this equation is to solve. I should clarify that a little bit. If the flow of the water is slow, it's very easy to compute the pressure. It's about three lines of equations. You can do it very easily. But what happens is as you force the water to go faster and faster, the water starts to wobble. And then those wobbles get bigger and they get bigger until finally the water is just going nuts and swirling around all over the place. That's the turbulent phase, and at that point we just don't understand anything about the water. The lovely thing about fluid mechanics is it's a very visual subject. You can show videos. You can't do that for quarks or general relativity. You can show videos for fluid mechanics. So let me show you a video of this. Let me firstly tell you what you're looking at here. This is a pipe. It has water flowing through it. The water is going to go that way. There's this weird black line through the middle. That's because there's a guy at the end here, just off the camera, dropping some ink in the water. And so what you're seeing with this black line is the ink moving with the water, and therefore showing you the water, the way the water is flowing. So what's happening at the moment? The flow is very slow. The water is just flowing in a straight line, and the fact this is just this ink just moves in a straight line is capturing that. So I'm going to press play, and as I press play, the water will speed up, and as we speed up, as we get faster and faster, we'll see what becomes of this line here. All right, so you can see as you speed up, it starts to wobble. But the wobbles are rather small. They're just some small perturbations. And then they get bigger. They seem to get frozen in the liquid at this point. And then as you go faster and faster, you can see that the ink is losing coherence. It's diffusing in the fluid. It's no longer a clear line at all. And then finally, as you get fast enough, it just seems like all hell breaks loose. It's not at all clear that there's some clear stream of ink. It's being buffeted all over the place by this turbulent water, just swirling around. The question is, how can we understand this behavior of the fluid in the turbulent phase? Here's another video. This one is not an experiment. This one is a simulation. Yeah, it'd be nice to have the lights low for this. Thank you. So let me explain what you're seeing here. This is a computer simulation of a fluid moving from left to right, and there's an obstacle that's been put in the way. The obstacle is just this square that sits here. And as it moves, we're going to start to see what happens to the fluid as it goes past the square. So there's a bunch of things to look at here. In particular, you can see there's some nice coherent structures. There are these vortices or eddies, which sort of appear fairly regularly as you move past. This is pretty well understood. It's called the von Karman vortex street for what it's worth. But as you zoom in, you can see that there's much more going on here. There's structure within the structure. There's big swirls and there's little swirls. And the big swirls sometimes disappear and sometimes they take off and have a life of their own, like this one. And the question of turbulence is to somehow get a handle on what's going on with this very, very complicated structure. And again, it's not something we can solve by hand. It's something where, at least on the level of solutions, we're relying on computers and serious numerical simulation to get a handle on it. But we'd like to understand what's going on with this. And you know, it's so complicated, it's not even clear what questions we should be asking. It's not like we can ever hope to write down a solution that looks like this. That's way too much. So it feels like probably we should treat this in some probabilistic sense, in some statistical sense. So the kind of questions that people ask are the following. So suppose that you know this bit of the fluid has velocity in that direction. What's the probability that the neighboring piece of fluid has the same velocity? Or what's the probability that the neighboring piece of fluid has a velocity that points in a slightly different direction? And how do those probabilities change as you separate the 2 points? That's the kind of question we would like to ask, and even better, like it's easier to ask than to answer. Really would like to answer it. Other questions. Swirling is clearly a big part of this story. You could just see there were swirls everywhere. What's the distribution of swirls? Are big swirls more likely than little swirls? When big swirls disappear, why are they disappearing? Are they breaking up into little swirls? What are those little swirls they're doing? Again, this is the kind of question that we would like to ask. It's been a very serious question for probably 100 years since turbulence research started seriously. And as with quarks, we've made progress in that time. We've understood some things, but there's still a lot that we do not understand about very simple properties of fluids when they flow very fast. In fact, being an outsider to this subject, it's sort of noticeable that the great breakthrough happened in the 1940s. The great Russian polymath Kolmogorov, who made many pioneering contributions to number theory and probability and computer science, he really understood the structure of turbulence in the best way that we have so far. This has been 80 years, and there's been much progress in 80 years, but it's clear that this Kolmogorov theory from 80 years ago is still the one that stands tall as the most important contributions to turbulence. It even looks like much of it isn't right. It's just the best we have at the moment because it's a hard problem. All right, so this is the question of turbulence. How do we understand this? We've seen the question of quarks, and so let me tell you what we're doing here. Why do we think that people who care about quarks have anything to say to people that care about fluids and turbulence? And the idea is that perhaps there's some relationship between these two phenomena. So you can see that, very roughly, if you really squint, it looks like maybe they're the same. Both of them have fields that are doing complicated things. This. They're not equal to each other. And these are different equations that we're solving. So they're definitely not the same problem. I didn't put an equal sign here. This squiggle symbol has a precise meaning for mathematicians, but for physicists, it's a really useful symbol. It means the thing on the left looks vaguely like the thing on the right. And that's sort of the question we're asking. Do these two things look roughly, and we don't even know if they're roughly the same. But at the very least, it's sort of clear that the toolkit that you might have to understand the fluctuating quantum fields might be similar to the toolkit you need to understand the fluctuating fluids. Talking about probabilities in both cases. There are some very clear differences. And the probabilities for the quantum fields are inherent quantum probabilities because quantum mechanics is not a deterministic theory. Whereas the probabilities for the fluids is because of chaotic behavior of the fluids, because we just don't understand well enough what's happening, and because sensitive behavior to initial conditions. So everything is, lots of this is different, but the hope is that maybe there's enough similarities to, certainly for us to talk to each other, and maybe for us to learn from each other as well. I have to say that my impression is, so it's only been 2.5 days of the conference. I missed today, 2 days of the conference. But my impression is that the toolkits we have are actually remarkably similar. I was quite surprised, actually. We're sort of really talking the same language in the both cases. I don't know if that's because we've both found the right toolkits, or just because humans have a lack of imagination when it comes to new things. But certainly, you know, as far as I can tell, people are able to talk across these two communities. Let me end with something that I think is a little bit speculative, but for me at least has been one of the highlights of this meeting. So it's something that's come out only in the last couple of years, but suggests that there might be more to this connection between what's happening on the left-hand side and what's happening on the right-hand side. And so this new thing, which may be completely unimportant in the big scheme of things, or maybe a great breakthrough, it's called the area law. So I'm going to tell you about the area law for quarks and then the area law for turbulence. So the area law for quarks is something that we've understood for a long, long time, since the 1970s, and it's the following. This is a space-time diagram. Take a quark and an anti-quark, and originally they can be together, and just pull them apart, and then put them back again. Okay? And ask what happens when you do that. And in particular, how much energy does it take to pull them apart and put them back again? So what happens? Well, we know from what I said earlier that the quark and antiquark have a flux tube between them. And so here's the flux tube just at some particular time when they're as far apart as possible. And that this flux tube costs energy. The energy is proportional to the distance between here and here. But of course, the flux tube was there for all time. It's not just there when they're far apart. There's always a flux tube. The flux tube is growing as you pull them apart and then shrinking again. So the better picture is the following, that actually the flux tube between the quarks first grows and then shrinks. And you can ask, sort of, what's the integrated energy it costs to do this? For those of you who know, a slightly better way of saying this is about the action, but I'll if you don't know what the action is, don't worry. What you do is you just multiply the energy times the time. So the energy is at every point proportional to the distance between them. So what you get when you compute the integrated energy is actually the area of this green oval. So there's the area law for QCD, or for quarks, is for physicists synonymous with the idea of confinement. It's just a way of capturing the fact that the energy grows linearly, and for reasons that I won't get into, it turns out to be slightly easier to talk about the fact that this thing called the action is proportional to the area that you sweep out. And the nice thing is that it doesn't matter what path the particles take. If they take some complicated path like this, and then you bring them back together, there's some minimal surface, a bit like a soap bubble that fills that curve. And it's that minimal surface, it's the area of that minimal surface, which is the answer that you get. Okay, so there's something in quarks that is to do with the area of things that move around. The new thing that happened only in the last few years is that there's suggestions that there's something very similar in turbulence. So the suggestion was made by Professor Migdal, who is sitting down here, and the work of the last few years is by Professors Kartik Iyer and Katapili Srinivasan and P.K. Jung. Two of them are also sitting down here. And the idea is the following, that you compute what's called the circulation. I have a complicated equation at the top there that's not in a picture frame, but basically you take the velocity and you integrate the velocity around the curve C. And what these very impressive numerics from a few years ago show is that the probability for the circulation around any given curve only depends on the area that fills the curve. Now, okay, two areas in two different theories. What to say? the connections between this, I think, are a little closer than they maybe appear at the level I'm giving this. In fact, Sasha Migdal was inspired by the ideas from quarks and QCD to propose that this area law might be might also hold in fluid mechanics. So as I said, it's speculative. Honestly, I don't know if this is a great breakthrough or if it'll just be a dead end. If you ask Professor Migdal, he'll tell you it's a great breakthrough. But I don't know. But that's just the way physics works. We're always chasing dead ends in physics, and some of those dead ends turn out not to be dead ends, but actually to be exactly the idea you need to make progress. So for me, this has been exciting to learn about, and I thought I'd share it with you as just an example of the kind of ideas that we're playing with at this conference. All right, I'll leave it there. Thank you very much for your attention.
I should probably also add that de Broglie pilot wave theory is certainly wrong. And I don't think anyone could deny that because it doesn't account for relativity, either special or general. That means it's at best incomplete. While regular mechanics has quantum field theory as its relativistic version, pilot wave theory hasn't quite got there yet. Quantum field theory pretty explicitly requires that all possible particle trajectories be considered equally real. Pilot wave theory postulates that the particle really takes a single actual trajectory, the Bohm trajectory. This is not consistent with quantum field theory, and so there isn't a complete relativistic formulation of Bohmian mechanics yet. But there is good effort in that direction. Now let's not even start talking about gravity. No version of quantum mechanics has that sorted out. Also, we can't ignore the fact that the initial motivation behind pilot wave theory was to preserve the idea of real particles. And I think we need to be dubious about that sort of classical bias. All that said, pilot wave theory does do something remarkable. It shows us that it's possible to have a consistent interpretation of quantum mechanics that is both physical and deterministic. No hoo-ha needed. Maybe something like pilot waves really do drive the microscopic mechanics of space-time.
It turns out that when large birds flap their wings, a circulation of air is generated. The portion that is rising is called upwash, while the portion that is sinking is called downwash. The lift provided by upwash is generated behind and to the outside of leading birds, which is a perfect place for following birds to hang out, reducing the work they have to do atop the mechanically generated cushion of air. To maximize the lift, not only do the birds get in line at a precise location, but they also flap their wings at the same time as leading birds. Should they drift into the downwash directly behind the leading bird, they flap at precisely opposite times, which is thought to reduce the effects of downwash for following birds. Since the lead bird has to do more work, leaders rotate positions to conserve energy, which distributes the workload more evenly. Now, it's not known whether the birds can simply sense these air circulations or if they may even be able to predict them, but the ability through which these birds have come to travel using such complex flight dynamics is as fascinating as it is surprising.
Bohmian mechanics doesn't use local hidden variables. Its hidden variables are global. The entire wave function knows the location, velocity, and spin of each particle.
We have eyes for vision, we have ears for hearing, but we have no organ that we know of that's involved in magnetoreception. It's a complete mystery.
For decades, researchers have tried to answer a simple question with a remarkably complex answer. How do birds find their way?
I had never thought that I would get to a place where we would start understanding the quantum mechanical mechanism that goes on inside the bird.
One of the greatest mysteries in sensory biology is how animals are able to sense the Earth's magnetic field and to use it to navigate.
Researchers have shown that some animals can indeed sense Earth's magnetic field, using it to navigate. But how birds like the European robin detect such a weak field has long baffled biologists.
It's the last sense we effectively know nothing about. And the solution of this problem, I would say, is the greatest holy grail in sensory biology.
And although the answer has remained elusive, researchers have put forward theories that they hope could explain this mystery.
Over 40 years ago, in the late 1970s, a physicist first dreamt up the idea that a light-sensitive molecule might be used by animals to sense the Earth's magnetic field.
This theory proposed that animals could sense magnetic fields using a quantum mechanical phenomenon called radical pairs.
The radical pair hypothesis suggests that you have a light-sensitive molecule, it absorbs light, and in the end you have a radical pair, so two unpaired electrons.
The magnetic spins of this radical pair can take on two states, both pointing in the same direction, a triplet state, or both pointing in opposite directions, a singlet state. The pair swings between these two states, but a magnetic field tips the balance, increasing the likelihood of one of the two.
And it's this change in the balance of the lifetimes of the triplet state relative to the singlet state which is thought to be the basis of magnetoreception.
And there was only one class of molecules that people knew originally could use light to generate radical pairs in plants, and they were called cryptochromes.
So Henrik and his collaborators hunted for these cryptochrome molecules in birds, and since cryptochromes need light to work, they searched specifically in bird eyes.
We found cryptochromes in the eyes of birds, and so did others. And then the big challenge was now, well, how do you now test whether quantum mechanic electron spin-based mechanisms goes on inside the eye of a bird?
The main barrier for the adoption of the cryptochrome hypothesis was that it was proposed by a physicist. So the mechanisms involved were highly quantum mechanical, very, very difficult for biologists to understand.
Henrik and collaborators from biology, physics, and quantum chemistry have worked to shed light on this cryptochrome hypothesis.
We needed to have the molecule in isolation to actually measure things on it, because it's very, very difficult to do it inside the eye of a bird. We started trying to make cryptochromes in 2004, and we now have 2021. At the moment, we are the only ones who have these molecules available for testing. And in Oxford, the groups are the only ones who can measure such molecule with the sensitivity needed to see what we have found. Not only could we show that the electrons jump inside the molecule exactly as predicted by the quantum chemists in theory, we could also show that the photochemistry of that radical was actually magnetically sensitive. Now it's not a hypothesis that this molecule is magnetically sensitive, we can see that it's magnetically sensitive.
The team were also curious how cryptochrome proteins compared between birds that migrate and birds that don't.
We then also made cryptochromes from an extreme non-migratory bird, basically the chicken. And it looks like the cryptochrome 4 from the migratory birds are significantly more magnetically sensitive than the same molecule from a chicken.
Previous work has shown that birds process magnetic field information in the visual region of their brains, and so Henrik and team members believe birds may actually see the Earth's magnetic field.
So maybe it's kind of a shadow on top of whatever else you would be seeing as a bird, but what exactly the bird is seeing we do not know because we cannot ask the bird.
But the puzzle isn't solved. The team have shown that cryptochromes are indeed magnetically sensitive, but they haven't yet proven that these proteins are the critical ingredient in magnetosensing in birds.
The advances that the authors have made in this study has brought us a long way to understanding how magnetoreception works. There's no question that the study was a spectacular piece of science, but because this is a laboratory study, it's not a study which is being performed on living animals, it's still no actual proof that cryptochromes in general are actually used in magnetosensing.
We are of course going to try to get closer to the natural situation inside the eye of the bird. Things like that would have been utopia before you could actually make the molecule in isolation, and we are very excited about the possibilities there.
I think, having studied quantum mechanics myself years and years ago, I would never have realized then, or even believed, I think, that it would be possible that quantum mechanical effects could be actually housed within the eye of a bird. That is a huge surprise, and that's nothing we learned in quantum mechanics when I was young.
How do you understand gravity in the framework of quantum mechanics, which we think of as, in some sense, the basic framework, the basic set of rules for doing physics in our universe? And of course, mostly you don't really need to combine these things if you want to build a better iPhone or whatever. It's not going to involve gravity. But there are certain situations. If you really want to understand black holes, if you want to understand how the universe began, understand what was the Big Bang, then you need a theoretical framework that includes both of these things. Okay. So just to remind everyone, I'm sure I don't need to do this, but when we talk about gravity, this is the Einstein version of gravity. So gravity usually has an I in it. It describes this is the dynamics of space-time and how it changes and interacts with matter. Okay, and of course, the central equation in classical gravitational physics is the equation of Einstein that says that if you have energy and momentum, and energy flow and momentum flow, well, this creates intrinsic curvature of space-time, and those are related directly like that. And so I guess part of the reason why fitting this into the framework of quantum mechanics is difficult is that the actual space that your physics is living on is dynamical. Okay, we very successfully took electromagnetism and combined it with quantum mechanics. It wasn't trivial, but it's been done, and the other interactions and forces in nature, we've combined them, and it all fits together very nicely in models that we'd call quantum field theory. So the standard model of particle physics is a quantum field theory, and that's a quantum mechanical system where the space-time is just fixed. But it's harder to incorporate gravity because there you need to actually understand the quantum fluctuations of space-time itself. Okay. So the field of string theory gave us a lot of progress in this direction. But I think in some ways, the first sort of truly complete model that came out of string theory, the first truly complete model of quantum gravity came in 1997. This was through the ADS-CFT correspondence of Moldacina. And what it says is that certain examples of theories of quantum gravity, so quantum mechanical theories that are describing this dynamical space-time, are actually exactly equivalent by some amazing connection to just ordinary quantum mechanical systems where the space-time is not fluctuating. So just to give you an idea of how that works, I'm sure you've heard colloquy on this topic before, but just as a reminder, so you've got an ordinary quantum system. Usually it takes the form of a quantum field theory. So you can think of something like electrodynamics where you have some fields, but now they're quantum mechanical. These examples tend to have very large numbers of fields. Okay. But just like any quantum field theory, you can have a state that's the lowest energy state of the system. So there's a quantum vacuum state. And the idea would be that somehow that corresponds, or that is encoding the information about a big empty space-time with nothing in it. We'll talk more about the details of what kind of space-time that is. I could also add in a little bit of energy. I could add in some excitation into my field theory. And so that would be a different quantum state of the field theory. And that might correspond to a small excitation in the space-time, like having a gravity wave go through there. Or I could add a lot of energy on the field theory side. And then on the gravity side, you could have something that looks qualitatively different. We know in gravitational physics, if you put in lots and lots of energy, you can form things like black holes. And so even something as exotic as a black hole is being described through a more or less ordinary state of the quantum field theory. It just happens to have a lot of energy in it. Okay. So that proposal has been around since 1997, and we now have, I think, more than 10,000 papers citing that original work. So in those papers, a lot of the papers were trying to find evidence to check whether this is true, whether it's consistent to make this connection between a gravitational theory and a non-gravitational theory. And so far, everything that people have done over those last 18 years has shown or has suggested that it's entirely consistent. But somehow, through all that, we still don't have a really good answer to why this works. So it's an amazing thing that through the quantum dynamics of a bunch of more or less ordinary fields, through some mysterious correspondence, you are actually describing gravitational physics. And so we'd like to understand, as a big, broad question, how does this space-time emerge from the story? And how does gravitational physics emerge from the story? And how are those things encoded in these more or less ordinary kinds of quantum field theories that are much like the standard model? Okay. So the really exciting thing that, I think, I'll give some of the history of this, but I think maybe started in 2001 and certainly in 2005, 2006, so certainly before I was interested in the subject. There's this suggestion that understanding not conventional field theory physics like scattering amplitudes and correlation functions, but thinking about the quantum field theory in the way that a quantum information theorist would think about it. So asking about things like entanglement, but in the context of the quantum field theory, and other quantum information quantities, that's a crucial step if we want to understand how gravity is emerging, how space-time is being described. Okay. So since it's a colloquium, I'm going to start really basic and just make sure that everyone remembers what entanglement is. And I'm going to start with a single spin. So this is the simplest possible quantum system. A two-state quantum system, and since I'm a theorist, that looks a little bit naked, so I'm going to put some clothes on it. So this is now referring to the state of this two-state system. So this is just describing a vector in the Hilbert space of a spin system. So this would be one particular state where the spin is up. And then, of course, the fundamental thing in quantum mechanics is that the set of possible states of that quantum system is a vector space. So you have basis states, and if I want to write the general state, I just take a linear superposition of these things. Okay, so this is the core property of quantum mechanics, that you have quantum superposition, that your states are in a vector space. Okay, so entanglement comes about when we think about systems that have more than one part. So the simplest such system would be going to the case where you have two spins, okay? And now the basic description of a system like that would be that each of those spins could be up or down, and that you could have these basic states up, 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 down, down, up, and down, down. But again, the most general state would come by taking a quantum superposition of those states. So mathematically, it's just a linear combination of these four things, which are vectors in the space describing the two-spin system. Okay. And so there's a crucial point. When I have a state like that with general coefficients A, B, C, and D, then I cannot generally write that as some factorized thing like this. So it's not true that when I write this down, I can't say, okay, the first spin is in this quantum superposition, and the second spin is in this other quantum superposition. It's just impossible to give a description like that. Okay, there are states like that, but most of the states do not have a description like that. And for most of these states where you can't write it like that, we would say that spin 1 is entangled with spin 2. Okay, so example, not entangled. This is in one state. This is in another state. Another one that's not entangled is this superposition, because I could factorize it. The second spin actually is definitely down, and the first spin is in this superposition. And then you have examples which are more generic where the two are entangled. So this up, up, plus down, down, you can't write it as the state of one spin and then the state of the other spin. Okay, so this is sort of a basic entangled state that we'll be thinking about. All right, so now I'm going to jump right back into quantum gravity, into the ADS-CFT correspondence. And I'm going to tell you about a paper that Juan Maldacena wrote in 2001. And this paper was something that, so when I had a sabbatical in 2009, and I decided to sit down and think about, well, how could I make progress towards these big questions of understanding this ADS-CFT correspondence? And I just wanted to see, well, what's the most interesting thing out there that I don't really understand, that seems different. And it was this paper by Maldacena. And in Maldacena's paper, so he was trying to think about, so remember we talked about different field theory states describing different spacetimes. Well, Maldacena wanted to describe a spacetime that has two what we'd call asymptotic regions. So imagine two big empty spacetimes, but they're not quite empty, because each one of them has a black hole in it. Okay? And these black holes are connected behind their horizons. Okay? So when you take a general relativity course and learn about black holes for the first time, you learned that a black hole geometry can be extended smoothly into into what we'd call a maximally extended spacetime, black hole spacetime, and it looks like this. Okay. So Maldacena said, well, how do you describe something like that using this ADS-CFT correspondence? And what he said was, well, since you actually have really, apart from that black hole, you have two separate spacetimes, there should actually be two of these quantum field theories involved. But there's something in the geometry that relates them, and it's this wormhole that connects the two black holes behind the horizon. But what Maldacena said was not that those two field theories have any kind of interaction with each other. The only relation was in his description of this space-time was to say that the two quantum field theories are in an entangled state. And he said that the field theory description of this space-time, according to the ADS CFT correspondence, is a state that looks basically just like that up, up, down, down state that we just wrote down for the spin system. What he said was, well, just write down all of the possible energy eigenstates of the field theory system, and then take this sum of states where it's vacuum state in one, vacuum state in another, superpose that with this state where there's a little excitation and the same excitation, and just keep going. And there are some coefficients there that I didn't write. But it's basically just a big entangled state like that spin system. Okay? So this is the remarkable thing. Just to summarize, he was saying, here's an interesting space-time where it's like two space-times except they're connected behind a black hole horizon. And he proposed, I won't give all of the arguments, but that this is actually going to be described in this correspondence by taking two completely independent physical systems and just entangling them in a particular way. Okay. So when I was thinking about that, I wondered whether, well, so what that suggested was that maybe, I mean, could it be that this entanglement in that example, is it the entanglement that's the crucial thing that connects the two spacetimes? And then what I was learning at the time when I was reading about more about entanglement based on that, and so I realized, or I didn't realize, but I read that when you just have the ground state of an ordinary quantum field theory, there's actually lots of entanglement there already. So even though with that example of Maldacena, you had to put the thing in a special state, and then you had entanglement between one field theory and the other, if you go back and just consider this completely vanilla state of a single field theory, the one that had the lowest energy and the one that was dual or corresponded to completely empty space-time, well, there's actually a whole bunch of entanglement in that state already. And so, for example, if you were to divide the space in half, you would find that the quantum fields on this side would be entangled with the quantum fields in that side. Okay, so in the room here, the electric field over here is entangled with the electric field over there. Okay. And so then this led me to wonder, well, could that entanglement have something to do with the fact that you've got this nice, smooth space-time? And so I thought about this thought experiment where you take that vacuum state and you just vary the state. So we're free to consider any state that we want in this field theory that's supposed to have a gravity dual description. And so I could consider like a one-parameter family of states where you start out with that very entangled ground state, and then you just arbitrarily draw a line halfway down the middle, and you start removing entanglement. You change the state so that now, in this case, there's a little bit less entanglement between here and here than there used to be, and here there's even less. And so what happened, I did this, I tried to do this and think about what would happen on the gravity side using whatever tools that were available. And what seemed to happen was that you had this big empty space-time, but then as you remove entanglement, it just starts to deform itself. It starts to pinch itself apart, kind of like you had a big wad of gum and you're just stretching it out. And what happened is that the two edges of the space-time are getting further and further apart. And in some sense, the middle of it is getting narrower and narrower, just like in the picture. Okay, so by removing the entanglement that was there in the field theory state to start with, then it seems that the space, this completely empty space, it actually starts deforming and ripping apart into two pieces. And then you could consider dividing your field theory into more parts and removing more entanglement between more of the parts. And eventually what seemed to happen was that your entire space-time just rips apart into tiny pieces and you have nothing left. Okay. And so in a sense, going backwards, that suggests, so this is all very qualitative, but it suggested that this classical space-time geometry that you had that was being described by the vacuum state of the field theory somehow maybe it emerges through all this entanglement between the quantum fields in different parts of space in the field theory picture.
Nature's webs come in all shapes and sizes, from dense shrouds to silken curtains, from creative chaos to perfect symmetry. They can look like waves and nets, slings, and deadly funnels. Of course, these intricate creations are useful for catching prey, but that's not their only purpose.
Spiders that weave webs often have very poor eyesight, and so they understand the world through the vibrations in their webs. So I've always been fascinated by spiders, and I was looking at how does the whole web vibration communicate information to the spider.
While this might sound like an inquiry into biology and nature, for Ross Hatton of Oregon State University, it starts with robots.
I study snakes and spiders and how they move and how we can use those ideas from how they move to make better robots.
So how do you get from web-weaving spiders to engineering robots?
We started off by building computer models of how vibrations travel through complex networks of strings. And in order to validate those models, we built the spider web.
The web needed to translate how a spider senses the world into a form humans can understand.
And our closest understanding of vibrations as humans is sound. And so how can we translate the vibrations that are happening in the web into sound?
This process is known as bioinspiration.
Bioinspiration is looking at animals and saying what are the things that an animal does that we might want to use as a starting point for engineering.
For example, real spiders use very stiff, strong silk for their web's radial lines, and stretchier silk for the spiral lines. To duplicate this 10-to-1 ratio, the team used parachute cord for the radial lines and shock cord for the spiral lines, the stuff hair elastics are made of. One of the next decisions was how large the web should be.
The clear answer for that was 8 feet, but that was a little bit too big to build, and so we cut that in half to about a 4-foot diameter.
Adjustable tuning pegs pull all the web strings into a uniform tension. Then, along came a spider.
A live spider can feel vibrations through its legs. And so when the web shakes, that shakes the foot. And so it's almost like we have an ear listening to each of these radial strands.
The team began exploring cues like direction, loudness, and pitch to get a sense of how spiders collect information. For direction, the model suggested spiders might do it pretty much like we do.
If you hear a sound and you look at it, you're balancing the sound between your ears. We can use that to center where the source is coming from.
Ross's spider looks for that balance between its feet.
With 8 feet, you can figure out which pairs of feet are centered on the sound. Once we've done that, we can combine that with the loudness to determine is it coming from in front of you or behind you. That gives us direction information.
But to find out exactly where the prey is, simulated here by a pluck, the spider shows that it has a musical side.
We have made it so that the big long strings play low notes and the short little strings play high notes. From that we can tell, did I pluck it far away or did I pluck it close to the spider?
The model may seem whimsical, but the complex mathematics behind it prove another instance where engineering and biology make good partners.